All right, let's go ahead and get into module number 2, exploring call signaling over IP networks. In module number 2, we're going to talk about the phone initialization process. We're also going to talk about single site on cluster calling and what's involved with single site on cluster calling, what types of protocols are involved, and how the communication process takes place. We'll talk about single site on cluster call setup, troubleshooting. We're going to talk about the call setup and teardown process, and then we're going to describe SIP call signaling for call setup and teardown. Then we have two different discoveries that we're going to be doing in this section. Discovery number 3, configuring and troubleshooting collaboration endpoints, and discovery number 4, troubleshooting calling issues. And then we'll wrap up this module by talking about call control protocols. We're going to talk about DTMF signaling over the IP network, that dual tone multi-frequency signaling over the IP network, and then we'll wrap up the whole module by going through our summary challenge. All right, so when it comes to communicating, there are a couple of different processes that are involved in order for a phone call to take place, right? There's a couple of different communication processes. First of all, there's protocols involved with the phone booting up, and we're going to talk about the phone boot up process and how it initializes. But there's also a communication process for doing call setup and call teardown. We have several different protocols that are available to us to do this call setup and call teardown, depending on how the phone is provisioned within Unified Communications Manager. There are two primary provisioning options that we have. We can provision the phone as a skinny phone with the skinny client control protocol, or we can use provision the phone as a SIP endpoint using the session initiation protocol. Once the call setup takes place, we have to establish the media stream. We use one protocol to transport the media. That's a real-time protocol. And then we also have to manage that media stream. And we manage that media stream with rtcp, the real-time transmission control protocol that allows us to identify the characteristics, if you will, of the call and you know what's happening with the call: packet loss, packet count, byte count, packets per second, jitter, and latency, and so on. Things that we're concerned about when it comes to processing voice calls on the network. So the first thing we're going to take a look at is what does a phone do when it initializes for the first time. All right. Now there is a specific order that of events that occur when a phone boots up for the first time, and there are some slight differences depending on how the phone is actually registering to the system. But the Cisco phone has a standard startup process that consists of several different steps. Step 1, power over Ethernet, right? Now, the Cisco phone obtains its power from the switch, or it certainly can obtain its power from the switch. We can also plug the phone into a wall with a power cube, or we can use some sort of power injector to inject power into the. But typically, the switch is going to be the one that's providing the power. Now, if we're using the IEEE standard power, the switch is going to continuously send a small voltage on the transmit pins. That voltage is sent by the switch. It's going to get looped back in hardware from the IP phone back to the switch's receiving pins. The switch has the ability now to detect that inline power is required for the device, and then the Cisco switch generates the port's default power allocation, which is typically about 15.4 watts. Well, the default power for Cisco proprietary power, what we call Cisco pre-standard power over Ethernet, is 10 watts. With the IEEE 802.3 AF inline power specification, the default power is going to be about 15.4 watts. Type B Cisco phones support IEEE power and the pre-standard Cisco power, but the IEEE specification didn't exist when Cisco was manufacturing the Type A phones. The 79X2 phones, the 79X5 phones, those are going to require the IEEE power, or at least a power brick plugged into the wall. The Cisco power option doesn't supply enough power for those types of phones. So, but you probably shouldn't run into a situation in today's configuration scenario where you're going to have a phone or a device that doesn't support the 802.3 AF or at least the 802.3 AT power specification. So that's step number one in this case. The switch is going to provide the power to the phone, and then the phone is going to boot up. All right. Step number two in the process, loading the stored phone image. The phone has NVRAM in it and non-volatile flash memory in it where the phone's firmware image is stored. So when the phone boots up, when it starts up, the phone runs a bootstrap loader that loads the phone image from the flash memory. And then using this image, the phone initializes its software and its hardware. All right. Step number three, the phone configures its VLAN. All right. The Cisco switch uses CDP, and we mentioned this in the previous section, also talking about LLDP as an option as well, the link layer discovery protocol. But we use one of those two protocols, either CDP or LLDP, to inform the IP phone which voice VLAN the phone should use for the voice over IP traffic. And actually, even though the port is configured as an access port, the configuration on the switch port would look something like this. We would go into the interface, we would type switch port mode, access, switch port access VLAN, switch port access VLAN 10, and switch port voice VLAN 100. That would be the basic configuration. Outside of configuring things like auto QoS or quality of service on the interface or other features like port fast and other spanning tree features, that would be the basic configuration that we would put on our access port with the phones attached. It's an interesting concept because actually there is .1Q tagging that is occurring on the port itself. The PC is plugged into the phone is plugged into the switch. The PC sends its traffic untagged into the phone, and then the phone will then send that traffic onto the switch untagged, which would then put that traffic into the data VLAN. The phone, however, does 802.1Q tagging, and it actually tags the voice traffic into the voice VLAN so that we do get .1Q tag traffic coming over to the switch port from the phone itself. All right. So even though we are doing .1Q tagging, the port itself is still configured as a host port or as an access port. We don't configure the port as a trunk port. Now, does that mean that you have to put the voice traffic into a separate VLAN? Not necessarily, right? It is a best practice standard because obviously we want to apply different configuration standards to the voice traffic separate from the data traffic. Different quality of service classifications and markings go on that traffic. Plus, we also want to provide additional security features for that particular VLAN as well. So we use CDP to tell the phone what VLAN it belongs to. There's an ASIC, or an application-specific integrated circuit, inside the phone's hardware that allows us to create the .1Q frames before we transmit that traffic to the switch port. The ASIC also gives the phone a 1P3Q1T quality of service configuration. That's 1 priority queue, 3 normal queues, and 1 drop threshold. Those QoS capabilities allow the phone to act like a 3-port switch. You've got the port that goes to the switch infrastructure, you got the port that goes to the PC, and then you have the port that goes to the phone ASIC that actually does the processing for the phone traffic itself. The Cisco phones do not support WRED, or what we call the Weighted Random Early Detection Congestion Avoidance Protocol, so that one threshold is set to tail drop. That last part of that 1P3Q1T QoS process is what the 100% Q utilization drop threshold that we have in the phone itself. All right, so we're using CDP or LLDP to be able to identify the VLAN that we belong to. The next step, step number 4, well, it's step number 5 in this particular case, we obtain our IP address. IP phones use DHCP by default to obtain their configurations, their IP address, their subnet mask, their default gateway, the TFTP server, option 150. We send out a layer 2 broadcast, the DHCP discover message, to a layer 2 broadcast address, all Fs, FFFFFF, FFFFFF. The DHCP server hopefully will receive that broadcast and returns an IP address lease from the DHCP scope in the form of an offer message. That contains the IP address, it contains the gateway, it contains the mask, the TFTP server option, and so on. If DHCP is not used in the network, we can do a static network configuration on the phone locally. If a DHCP server doesn't respond, the IP phone will actually make use of the DHCP scope that is actually stored in NVRAM. So there is a stored scope within NVRAM, but that would only be if the phone had previously obtained a lease from the DHCP server. All right, so we get our IP settings. Step number 6, we move into requesting our configuration file and our profile file. All right, the TFTP server in our particular case has this configuration information. That configuration file includes the parameters for connecting to Call Manager or Unified Communications Manager, and information about which image load a phone should be running. All right, the first file that the phone is going to request is what we call the Cnf.xml file. It is the SEP, it starts with SEP, and then it has the MAC address of the phone, .cnf.xml. SEP comes from Celsius Ethernet phone. This technology was acquired from a company called Celsius, and all of the phones had the designation a Celsius Ethernet phone. So we've kept that, or Cisco has kept that throughout the entire process. So that's why you always see an SEP in front of the MAC address to identify each phone individually within the Unified Communications Manager configuration. So SEP, the MAC address, .cnf.xml from the TFTP server. Now, if for some reason the TFTP server doesn't respond, the phone will fall back to the latest configuration that it has stored in NVRAM. If the TFTP server does respond, but the SEP MAC address cnf.xml file isn't found on the server, the phone requests the XML default.cnf.xml file. That XML default cnf.xml file is used to request the auto registration configuration information. Now, we'll talk later on about how to provision phones within Unified Communications Manager. One of those provisioning techniques is to use auto configuration, but auto configuration is actually, or auto registration, excuse me, is actually disabled by default within Unified Communications Manager. All right. If it is enabled, Call Manager will actually dynamically generate a directory number and a configuration file for the phone if auto provisioning is configured or auto registration is configured and the phone is actually able to provision itself. If we have cryptographic features enabled on Unified Communications Manager, the phone is going to attempt to download the CTL, the Certificate Trust List, in addition to the phone configuration file. All right, so that's the next step in the process here. So now we're at the point where we get to register the device. We've already gone through step 7, downloading the phone load, the local, well, actually, I didn't actually quite talk about step 7. Step 7 is where we would download the actual firmware for the file. I mentioned it briefly, but let's talk a little bit more about it, because the phones will ship with firmware already installed on them. All right, depending on how the phone was provisioned, how old the phone is, when you did an upgrade on your system or whatever, will depend on whether or not the phone needs to download additional firmware. Now, there are two places that we can define what firmware is supposed to be used for the phone. There's a place called Device Loads, which is under the device configuration screen, or there you can specify the firmware that you want to use for the phone under the phone configuration profile itself directly. All right, but if the firmware that's running on the phone does not match the firmware that's specified in Unified Communications Manager, whether it's an upgrade or whether it's a downgrade, the phone will apply that firmware. It will receive that firmware through TFTP as well. Now we move into the registration process. The configuration file itself includes a prioritized list of Unified Communications Manager servers that are configured in something called a call manager group. And we can define up to 3 servers within that call manager group: a primary, a secondary, and a tertiary server. Once we've obtained the file, the configuration file from the TFTP server, we attempt to register with the highest priority call manager in the call manager group using SCCP if it's a skinny phone, if the phone has been provisioned as a skinny phone. SCCP uses TCP port 2000. The boot sequence for SIP phones is really very similar to a skinny phone, but there are 3 major differences. The first difference is the SEP Cnf.xml file. The SIP phones get their entire configuration from the configuration file. So the SEP.cnf.xml file for SIP phones is much larger than a skinny phone. The dial plan file could be downloaded as well. Cisco SIP phones can download and use what we call local dial rules or local dial plans. Third-party SIP phones can actually be configured with local dial plans as well, but they can't be configured and downloaded from CUCM. They have to be, the third-party phone configuration takes place directly on the device itself. And then additionally, SIP phones have the ability to download the soft key file. The SIP phone download will download its soft key sets in an XML soft key file, whereas the skinny phones receive those soft key states as part of the call control signaling process. All right. Now, as I go into the boot up process here, I'm going to talk about, some of the similarities between them, but I already kind of pointed out some of the differences here. So let's take a look at the phone initialization process, and that'll be kind of the last thing we talk about here. All right. Now, as I mentioned, it is going to be slightly different for an SCCP phone as opposed to a SIP phone. The SCCP, the first initial steps of the SCCP boot up process are identical between SIP phones and skinny phones, and then the steps following that are going to be slightly different. All right. And I'll point out what those differences are as we kind of go through the process. So the first step is the SIP phone. Let's talk about SIP initially. The SIP phone boots and downloads the CTL file from the TFTP server. That CTL file contains a set of X.509 v3 certificates that's used when you have Cisco Unified Communications Manager cluster security enabled. Cluster security we will talk about a little bit later on as we get into the process of talking about securing the Unified Communications Manager platform. The SIP phone requests its SEP Cnf.xml file from the TFTP server. Again, if the phone is new, it's not going to find that information. It's going to have to use the default configuration in that particular process. But eventually, once the phone registers, it will create that SEP mac.cnf.xml file from the registration process. We're going to download the default configuration file. That default configuration file is called xmldefault.cnf.xml from the TFTP server. That basically contains, again, all of my basic configuration parameters. The location of the call manager, the location of the phone, auto registration requires this phone. But again, the auto registration feature is not enabled by default. So the file has to contain a parameter called auto_registration_name. If that parameter is not established or that parameter is not set, then the phone will not attempt to auto register. If that parameter is not empty, if that parameter is configured, the phone will go ahead and auto register, and it finishes the boot sequence, and we'll get a directory number assigned, and so on. All right. Step 4, the SIP phone requests the firmware upgrade. That's what we call the load information. If one was specified in the configuration file, this process basically allows the phone to get its load information. All right. And the process basically allows the phone to upgrade its firmware image, allowing it to operate with, an upgraded version of Unified Communications Manager or whatever it might be. Maybe we're applying a firmware update because there was an identified bug or issue with a previous firmware version. All right. Each time, by the way, that you do update Unified Communications Manager, each time you update Unified Communications Manager, the additional or new firmware will be part of that package. All right. All right. After the image was downloaded, after we've authenticated with the Cisco self-signed X.509 v3 certificate, the phone reboots. It's going to load up its new image. And it might actually take a couple of times. You can see some progress indications on the screen of the phone. It will indicate, what stage it's at in the upgrade process, and because it doesn't do one basic upgrade, it will do incremental upgrades as part of the process. Again, the phone will get a list of ordered call manager servers that it's supposed to register to. The highest one in the list is the one with the highest priority, and then the configuration file indicates how SIP should be controlled. The default control protocol, of course, is SIP, which is going to run over UDP port 5060 or TCP by default. The TCP is only going to be supported in Type B phones, not Type A phones. The booting for a Type B phone is a little bit different from what we described here for the Type A phones. The Type B phones have to actually first download the SIP default.cnf file, and that contains the default configuration parameters that are shared by all of the SIP phones that use that particular TFTP server, and then the SIP phone continues requesting the SIP mac.cnf file to get its individual configuration. All right. All right. Let's see. They mentioned a couple of other things here. Let me just scroll down. I kind of summarized most of this process already, but they mentioned if the SIP phone does not have a provisioned directory number, we talked about the auto registration process. Let me see here. If the parameter does contain an auto registration name, that name is used as the directory number in the SIP register message that gets sent to the SIP UA or the SIP proxy, and then we can identify, the configuration. And they mentioned a couple of bullet points here. Identify that the special auto registration name has been used. Create an entry in the database for the new phone that is based on the current auto registration settings. Generate the SEP Mac Cnf.xml file for the phone. Accept the registration with the 200 OK. Notify the phone to get the configuration files again. And then the phone will automatically reset and reboot. All right. How many Cisco call managers can be prioritized in the prioritized list found in the configuration file? As many as needed, 8, the maximum number of nodes in a cluster, 20, the maximum number of servers in a cluster, 3, primary, secondary, tertiary, or 5, primary, secondary, tertiary, and 2 backups. So the answer to this question is 3, and that is the call manager group. That's how we define that limitation. DHCP will send the IP address of the TFTP server to the endpoints using which scope option? Now, this might look different on the exam, guys. It's option 150. Option 150 is the Cisco proprietary option that's used for defining TFTP, but you can use option 66. That is the standard or the open standard option for specifying a TFTP server. Cisco phones will actually respond to both options, not just option 150. There are some reasons why you may decide to use option 66 over option 150. We'll talk about that a little bit later on. All right. So now let's talk about what types of protocols are involved in the process of communicating if we have a single site on cluster calling, meaning that we're calling from phone to phone within a cluster. We're not sending the traffic over a trunk. We're not sending the traffic to the PSTN. And we can see that there are several different protocols that are involved in this communication process. We've got SIP and SDP. We've got Xmpp and SIP and Simple. And we've got RTP, RTCP, SRTP, as well as H239 and binary floor control protocol. So let me go ahead and break down some of these different protocols. So let's start with SIP. We didn't mention Skinny in this particular case because, quite frankly, the Skinny client control protocol is, first of all, it's proprietary to Cisco, and as such is not as widely used nowadays, although it is still supported. We're starting to see Cisco shipping phones that only support SIP as a control protocol and not Skinny anymore. So we tend to focus most of our attention in our discussions on SIP. SIP is the Session Initiation Protocol. It is a call control and signaling protocol, and we use it to initialize or maintain or terminate voice and video calls. I mean, it's used for other things as well, like messaging applications and so on, but it is a call control protocol. It is used for controlling the communication sessions between our endpoints, our phones and our gateways and trunks as well. All right. The protocol defines a very specific format of messages that get exchanged and a different kind of sequence of communication for the endpoints that are participating in that communication protocol, right? It is a text-based protocol. It incorporates a lot of the different elements that we see in the hypertext transfer protocol, or HTTP, as well as the simple mail transfer protocol, or SMTP. All right, so there are lots of different control messages that get sent back and forth. In fact, there may be multiple media streams that are created, but we'll talk about how the media streams are established a little bit later on when we get into our discussion about RTP. But SIP does work in conjunction with other protocols as well. In fact, we mentioned the session description protocol here as well. I'll get into the session description protocol in a minute. We always kind of see SIP and STP classified together. All right. Now, the STP information is actually carried inside the payload within the SIP message. It is kind of SIP is kind of designed to be independent of an underlying transport protocol, but it is used primarily with UDP, or it can be used with TCP, or it can even be used with SCTP, which is the Stream Control Transmission Protocol. If we're trying to do, say, for example, transmissions of SIP messages over a secure network. All right. Now, the protocol itself contains multiple signaling operations to establish the media communication session. And again, the concept, and we see this with MGCP, we see this with H323, we see this with SCCP, we see this with SIP. The protocol itself is used to set up and terminate the call itself, as well as to control intermediary functions that are happening during the call. If you put a call on hold, if you do a call transfer, if you hang up the call, that kind of thing. All right. So it allows not only the call setup and call teardown, but it also allows for the modification of the existing call itself. It is completely separate from what is carrying the actual media. The media is going to be carried by RTP, the real-time protocol. We'll talk about that protocol a little bit later on. All right. Every SIP network, you know, whether it has UAs, user agents, it has voicemail, it has call routing functions, they're going to be identified by something called a SIP URI. URI is a Uniform Resource Identifier. And the syntax of the URI is kind of what you would typically see in like an email address, right? So SIP : username at domain.dom, or SIP : username at this port, whatever. If you have a domain name, if you're using a domain name with the URI, that's going to require a DNS server record. If you're doing the port, the host port option, that's going to be typically an IP address or the fully qualified domain name of that particular host and port. If you're doing SIP secure transmissions, we use SIP-S. That's SIP with basically TLS or SSL. All right. So SIP uses a very similar construct to what an HTTP request and response transaction would look like. Each transaction actually contains requests that actually engage particular functions on the server and would elicit at least some sort of response from that server. So SIP actually reuses most of the header fields and a lot of the different encoding rules that we see with HTTP. It's a little bit beyond the scope of this class to get into the specifics of that encoding method. I might talk a little bit about some of the message formats here, but obviously we have a lot to talk about, so we'll continue on. SIP usually will run over TCP or UDP, either on port 5060 or 5061. Port 5060 is typically going to be used for your non-encrypted signaling traffic, and port 5061 is going to be typically used with TLS or your encrypted traffic. All right. Now, as far as the network elements, SIP does use something called SIP user agents. Each user agent is what performs the function of what we call the user agent client. So if it's requesting a specific service function and we send that request to the user agent server, and then the user agent server then responds to that particular request. All right, the user agent is basically the endpoint that sends or receives the SIP messages and manages the actual SIP session. They have both client and server components, but we're usually sending the UAC component sends the SIP requests, and the UAS component receives the requests and returns various responses that are necessary. All right, we don't have, in other words, fixed roles of client and server, like in HTTP, where the web browser acts specifically as the client and never as a server. SIP requires that the peers that are communicating actually implement both the UAC and the UAS role in the process. Okay, if it's an IP phone, it's going to implement the client and server functions just like any other device. Okay, now we also have a SIP registrar. A SIP registrar is the SIP endpoint that provides things like location services. It accepts register request messages. It records the address and the parameters from the user agent that's actually doing the registration, and then any kind of subsequent request after that, we provide features and functions for that. All right. Now there are some other components. You can have a session border controller. You can have a SIP proxy server. You can have a redirect server, but I'm not going to get into those specifics here. I do believe that we're going to spend some time talking about the control messages in more detail a little bit later on. As I mentioned before, SIP is a text-based protocol. Syntax is really similar to HTTP. There are basically two different types of SIP messages that you're going to see: requests and responses. The first line of any request has a method that defines basically what the request is. So we have a request URI that's also listed there. That request URI tells us where that request needs to be sent. And then the first line of the response has what we call a response code. So as far as request options go, you have a register request, you have an invite request, you have an acknowledgement request, a buy request, a cancel, an update. What are some of the other? Oh, subscribe. You have a subscribe as well, a message, and there's some others as well. I think there's about 4 or 5 others. I can't remember all of them off the top of my head, but those are some of the most common ones. Obviously, the register request is we're trying to register the URI in the to header field with that location server. Invite, we're trying to establish a call. So we're trying to set up a call. An acknowledgement would be confirming that we received that response. Buy would be like a signal termination. Update would be we're modifying the state of a session. And a subscribe, we're initiating a subscription for a notification of events. We see that with like DTMF and whatnot. And there's some other components as well. We will get SIP responses as well. Responses are sent by the user agent server, indicating basically what happened with that particular received request. We actually classify responses into different classes, and this is very similar, like I said, to what we had with HTTP. Any code, these are 3-digit codes that you're going to get, you know, like a 404 code or a 500 code or so on. We have similar codes within SIP, right? A 1XX code means that, you know, we kind of accepted this request. It's a valid request, and we're going to go ahead and start processing it. A 2XX code indicates that we successfully completed a request. A 3XX code means that there's some sort of call redirection needed for a particular request, and that response code might actually include information about the new destination. A 4XX code means that we cannot complete the transaction. Could be a bad request syntax. Something is not. We can't find something. A 5XX code means that the server basically failed to process the request. It was at one point a valid request, but we failed to process the request. All right. And 6XX code, that means that the request can't be fulfilled by anybody. All right. So there's certainly a lot more that we could talk about with SIP. You know, it's a little bit beyond the scope of this class to really get into all of these details, but you know, let's go ahead and talk about the next protocol on the list, which is SDP. All right, now SDP, or the Session Description Protocol, describes the multimedia communication session it provides us the ability basically to do session announcements and session invitations. It is a way for us to extensively support, if you will, different media types, different media formats, and was originally part of SAP. I don't know if you guys ever worked with SAP before, the Session Announcement Protocol, but it's obviously very useful for managing real-time transport or RTP, real-time streaming protocols, as well as SIP in this particular case. Session description basically just describes the session of the call with different formats, right? It's going to include various components about the call, right? V would indicate the protocol version number. O would indicate the originator of the session information. S would indicate the session name. Things like Z would indicate like the time zone, and so on. We're also able to identify things like what type of media is being used in the session itself. Unfortunately, on the exam, they do ask you quite a bit about this particular protocol. And how they give you a lot of outputs, screen outputs, and they'll say, okay, based on this screen output, can you identify what type of call is going to be used, or what type of call is being used? So for example, if I have an M equals audio 49170 RTP AVP, that means something, right? That means that the first that the audio stream is on port 49170 using payload type 0. That would be PCMU. And by the way, those different payload types are identified in a specific RFC. I think it's 3500 something. I can't remember the specific number, 3550 or 3551 or something like that. If I have a payload of type of 99 as an example, that would be a dynamic payload. Unfortunately, you have to use or you have to know what those specific types are. We'll see a reference to that a little bit later on. All right. Now, the next protocol that we see listed here that we're going to talk about is the real-time transport protocol. This is my media encapsulation protocol. It's the actual protocol that delivers the audio and the video over the network. It's the protocol that carries the payload. All right, it runs over UDP. It actually uses a range of ports. It's 16,384 to 32,768. It uses the even numbered ports, and it actually works in conjunction with RTP control protocol, the rtcp protocol, which is the real-time protocol control protocol. That's the sister protocol for RTP. RTCP is it provides basically out-of-band statistics and control information for the RTP session. It basically provides feedback to the phone, to the endpoints, to the administrator, whoever is looking at the information on the quality of service in the media distribution by sending these statistics like how many bytes have been sent, how many packets have been sent, what is the packet loss, what is the packet delay and variation, which we call jitter, what is the round trip delay time, to the endpoints that are participating in the session itself. That information can actually be readily viewed on the actual screen of the phone. And the idea is that we can use that information then to control the quality, the service parameters of the call. We can switch to a different codec, and so on. RTP is usually going to use the even-numbered UDP ports. RTCP will be sent over the next highest odd-number port. All right. Now, RTCP itself doesn't actually provide any flow encryption. It doesn't provide any authentication. That would be done with secure real-time transport protocol. But again, the basic function or the primary function of RTCP is to just give you statistics and quality aspects of that media distribution during the active session and then transmit that data to the endpoints that are participating in the call. All right. If you're running, for example, an adaptive media encoding codec, and we are detecting transmission faults, we can actually move to a different codec in that particular case. All right. The bandwidth that's required for RTCP shouldn't really be more than about 5% of the overall session bandwidth. So it's a relatively benign protocol. It doesn't really, it's kind of a basic protocol. There are some components to it, different message types. We have a sender report, we have a receiver report, we have a source description, a goodbye message, and so on. But we don't need to get into those specifics in this particular case. All right. So again, RTP is actually used to carry the media streams, audio and video. And by the way, RTP is independent of the control protocol. RTP is the same type of RTP, and RTCP function is used with SIP, it's used with Skinny, it's used with MGCP, it's used with H323. It is essentially the primary protocol for carrying this information. It's part of the AV working group of IETF. It's been around for a while, since the mid-90s. And I think RFC 3550, now that our 3551 is the one that defines STP information, 3550 is the one for RTP. It is an end-to-end protocol, and it is used for real-time transmission. You know, if we're doing YouTube videos or we're doing some sort of stored video or stored audio, RTP is not typically going to be used to deliver that type of information. All right, the protocol itself does have components built in, even though it runs over UDP, to do things like jitter compensation, to detect packet loss, to identify what happens when we have out of order delivery, and so on. But it is the primary protocol for transmitting our media streams. All right, it is a relatively benign protocol itself. It's only got I think it's a 12-byte header. The RTP payload size will depend on what type of encoding you're using, but as far as the RTP header itself, it's a relatively small packet header. It's 12 bytes. RTP header is 12 bytes. It's got a version field. It does have a payload type field, which allows us to identify the type of payload. And it actually has sequencing and timestamps. There's a 16-bit sequence field in RTP that will increment each time RTP data is sent back and forth, so that the receiver can identify packet loss and so that we can handle some sort of out of order delivery. All right, the initial sequence number, just like with TCP or UDP, is going to be, well, not UDP, but TCP, is going to be randomized, and then their subsequent sequence numbers will be based on the information that's sent. It also has a timestamp, so there's a time interval to indicate the timestamp of that. Especially the timestamp is pretty critical as well if you're trying to do synchronization with audio and video and so on. All right. We don't need to get into much more of that. You're not going to be asked on the exam about the format of an RTP header, but understand that RTP is used to carry this audio information. SRTP is just basically the secure version of RTP in this particular case, the secure real-time transport protocol. It supports all of the cryptographic extensions, and supports things like encryption, message authentication, integrity, replay attack protection, and so on. All right. There is a sister protocol to SRTP, SRTCP, obviously, because we still have to have the rtcp component, if you will. All right. All right. Let's talk about Xmpp now, the Extensible Messaging and Presence Protocol. I'm kind of just going around the circle here, trying to give you as much information as I can. Xmpp is also a communication protocol for real-time exchange of information between parties. Originally, the protocol was called Jabber. Cisco kind of confused everybody when they created a client called the Jabber client, but that's why it was originally called the Jabber client, because Xmpp was originally called the Jabber protocol. It's the Extensible Messaging and Presence Protocol. All right. Now, Xmpp is an open standard. It's not Cisco proprietary. And the goal of Xmpp is to provide basic real-time information about the presence of an individual. You know, are they available through various communication methods? Are they available through chat? Are they available through phone, voice conversation, and so on? It does support things like instant messaging. Of course, it's going to provide presence information. Basically, presence information gives us the status, the ability for somebody to communicate with a partner. And again, depending on what type of communication techniques are available, will depend on how you can communicate to that particular individual. We can also do a push subscribe type of component. We can do file transfer, we can do gaming, all kinds of things with Xmpp, but we'll talk more about Xmpp in more detail a little bit later on. All right. All right. Let's see. Do I want to mention anything else about this particular protocol? I don't think I'm going to right now. We'll again talk about this protocol in more detail when we get into the presence discussion a little bit later on. There is another instant messaging based protocol called Simple. That's the Session Initiation Protocol for instant messaging and presence, blah, blah, blah. I don't remember specifically. I think it's for something extensions. I can't remember what the L stands for, leveraged or leveraging or something like that, but it doesn't really matter what the acronym is, but it's basically the same type of protocol as Xmpp. It is a presence protocol. It is also an open standard presence protocol that can be used. It applies SIP in this particular process, though. So that allows us to register presence information, to receive notifications if an event occurs, that kind of thing. We can also send SMS messages through the process and perform other presence functions as part of the communication protocol. All right. H239 is another kind of a communication protocol. It's actually an ITU-T standard. It's part of the H320 or H32 standards of protocols, even though it's 239. It builds on those particular protocols. It was actually introduced by Tandberg and PictureTel, I believe, but it's mostly a video conferencing protocol, and it, without getting into the specifics, it establishes a way of signaling between different gateways, between, say, H323 gateways and H320 gateways and so on. This is typically used whenever you're using an H323 call. Now, signaling is usually defined in H245 when you're establishing an H323 call to set up what we call the capabilities of the connected endpoints in that particular call. If those capabilities include H239 presentations are supported, then we can choose to open up a separate video channel to do presentation functions within the video call. And we're really talking about the ability to push presentation information over that particular call. I don't know why they specifically call out this particular protocol. I'm not sure why they you know, it's very specific to video conferencing, but I guess they're just trying to give you an idea of you know, a different protocol that's available, like BFCP, the Binary Floor Control Protocol. Also another protocol that's used to push video information over the over a session. In the book, they mention it very briefly, right? Let me scroll down, and I'll just kind of go through these two descriptions, and we'll call this done, right? H239 is a protocol. It's an extension to the H323 family of specifications to allow a second video stream in parallel with the primary live video stream, so content like slides and spreadsheets can be shared. The second stream is a one-way and considered important in video conferencing, where I can see the speaker and in parallel a presentation of slides. You need an MCU, a multi-point control unit, to control that conferencing mode. And then BFCP, the Binary Floor Control Protocol, does basically the same thing. All right, allows us to send media. Floor control enables applications to provide users with shared access to different resources. And again, I'm not sure why they're bringing up these two particular protocols when we're really talking about, you know, call control and call signaling. This is more of a video-related signaling component. So I'm not going to get into as much detail on those two as we did with the other ones. All right. Which protocol collects information regarding the availability status of communication capabilities of a user to determine the presence status of that particular user? Well, that would be Xmpp. We already talked about SDP. Well, we talked about all of these, and none of those are related to providing presence information. Either Simple or Xmpp would be the appropriate choice in this particular case. All right. All right. Now let's talk about what happens if something doesn't work, right? When a call is set up in Call Manager, there are various functions that take place, and there are different reasons why call progress would fail. Maybe the phone is, the endpoint that I'm dialing is not registered. Maybe the dial plan is not being manipulated correctly. You know, so the call is not proceeding because the numbers are not being presented in the format that they're supposed to be presented in. Maybe there are some QoS settings that have been established in the communication channel that disallow the call because of call admission control, or maybe there's just poor call quality because we've oversubscribed a link and we don't have the appropriate quality of service settings in place. I mean, there's all kinds of things that could cause a particular call to fail. All right. Maybe you have a translation pattern and you're manipulating the digits incorrectly. You're prefixing a 9, or you're not removing the 9 or whatever. The destination device might not be registered. Maybe the call is pointing to a gateway or a gateway resource, and that gateway, the IP connectivity to call manager's up. Maybe it's a cube, a border element, a Cisco Unified Border Element device, and it's got a SIP trunk going to an ITSP, but the SIP trunk side is down, but the communication, the SIP trunk to call manager is up. Maybe calling privileges are not configured correctly, right? You're not in the right search space. You're not in the right partition. Well, search space would really be for outbound dialing, defining what you're able to dial and so on. Maybe different codecs need to be used. Maybe you need some sort of transcoding resource. A transcoder is a hardware component that allows me to convert a call from one codec to another. Maybe the endpoint that I'm communicating with doesn't support the codec that I'm natively configured with. Or maybe I'm running a G711 codec and the destination requires a G729 codec, which means I have to do some sort of hardware transcoding in that path. By the way, that particular problem, the call setup and call teardown would work just fine. The call would actually ring through. The end user, the recipient, would actually pick up the phone, and then the call would fail because the transcoding has to be done on the media stream. So call setup and call teardown are separate from actually coding and decoding the media stream, which is an RTP issue. So almost 99% of the time when I've seen an issue with the call proceeding, so I can dial the number, it tells me I don't have a dial plan issue, I can make the call proceeds, the person hears the phone ringing, and then the call picks up, and then the person picks up the phone, and then the call all of a sudden drops. And if I don't get a message on the screen that says not enough bandwidth or whatever, that would typically, by the way, happen. The call admission control failure would happen in the call setup process. So if the WAN doesn't have enough bandwidth or the call can't proceed because there's not enough bandwidth, the call won't even actually ring through. But if it's a transcoding issue, a codec mismatch issue, the call will look like it's going to proceed, and then it will hang up as soon as we try to establish the RTP stream. Another thing about RTP that I didn't mention as I was talking about the protocol is that those are one-way sessions. There's actually two different RTP streams that are set up for every call. One in one direction and one in the other direction. So it is entirely possible that you could have one-way audio where RTP is going or flowing in one direction, but it's not flowing in the other direction. And that could be a security, a firewall configuration, or some sort of security issue that's blocking RTP in one direction but not the other direction. I mean, there are basically a whole bunch of different types of things that could occur to cause problems. All right, endpoint registration. Maybe TFTP is not configured correctly, or it's pointing to the wrong TFTP server. Maybe DHCP is not set up correctly. If there's a codec mismatch, for example, we just talked about that. DTMF, dual tone multi-frequency. When you're pushing the buttons on the phone, if you're going through an auto attendant or some sort of call handler, those buttons generate dual tone. It's called dual tone multi-frequency because there's actually an x-axis and a y-axis of frequencies, and they get combined together to create the DTMF tone that's used to process or to indicate that that particular button is being pushed. Well, DTMF isn't always carried inside of the RTP stream. Sometimes it's carried outside of the RTP stream. In SIP, for example, DTMF could be carried externally from the SIP, from the RTP session. So it's a possibility that those DTMF messages are not being sent back and forth. All right. So let's talk about the codec negotiation process. And what you're seeing here in this section is you're seeing a configuration of what we call regions. All right. There are two things within Unified Communications Manager that we use to configure locations, to configure call admission control and codec selection. One is called locations and the other is called a region. Now the location will allow us to define how much bandwidth can be used when I'm calling from one site to another. And we'll get into this more as we get into the configuration pieces a little bit later on. But when you're setting up a location like HQ or branch 1 or branch 2, you can define how much bandwidth is available for calls between those locations. The region information is what allows me to establish what codec is going to be used for communicating between different regions. So the way that you read this is the region that we're configuring, and we're saying, okay, if I'm going to call from branch 1 to branch 1, so if it's a phone in branch 1 and I'm calling another phone in branch 1, for audio, I'm going to use this codec, G711 or G722. We kind of classify those together. All right. And then there's a video component as well. If I'm calling from branch 1 to HQ, I'm going to use the G729 codec. So the region allows me to define what codec should be used, between the different regions that are defined within the Unified Communications Manager. Location is the total amount of bandwidth. The region is the type of codec that's going to be used. All right? And that will depend on the region. The region is actually going to be established and configured as part of the device pool configuration. So let's see here. Let me go back to this diagram. So you see here the device pool. Phones get assigned a device pool. Notice all of the things that get associated to the device pool. Region, call manager group for primary, secondary, tertiary call manager, location, network locale, SRST. This diagram here kind of defines all of the dependencies that we configure within call manager. So in order for me to configure a device pool, I would want to configure all of these components first. In order to configure a media resource group list, I needed to configure a media resource group. And in order to configure a media resource group, I have to have media resources configured. That's what this call out diagram basically references, is all the dependencies on that we have within call manager when we're defining various components. It's relatively up to date. I mean, I started creating that diagram. I created that diagram from scratch, but I started creating that diagram when I first started teaching about call manager, and it was 4.x at that time when I started teaching it. But anyway, the region configuration gives us the permitted codec for that particular region. So when I place a call between two different devices, depending on how the region is configured, the two different devices will use the best codec that both devices support, but doesn't exceed that configured codec bandwidth for that particular region configuration. Now, if the two devices cannot agree on what type of codec to use, say one region says you're only allowed 8 kilobits a second, but the device only supports G711, that's when we have to use a transcoder. And if the transcoding resource isn't available, that's when the RTP audio stream will fail. Okay, so the regions and locations are what we use to basically define how the call is going to proceed. All right, in this diagram here, we see two phones on the left. Phone A supports AACLD, G711, and G729. Phone B supports G711 and G729. The region permits all codecs, including AACLD, but because Phone A and Phone B have to select a common codec, they're going to select the best possible codec based on essentially the bandwidth and the mean opinion score. G711 has a higher mean opinion score. It's a higher quality codec, so both phones are going to go ahead and use that particular codec. Now we have the same two phones on the right, but the region was configured to only allow G729. So the phones will select G729, first of all because both phones support it, and secondly because that was defined by the configuration. All right. If you don't have compatible codecs between the endpoints, if they don't have a common codec, the call will only work if you have defined a transcoding resource. And you'll notice here that transcoders is one of sorry, my batteries died. If you don't have a transcoder and there is a codec mismatch, like I said, the call will proceed. You'll get the call will ring through, and the person will pick up the call, but as soon as you pick up the call is going to die because we can't establish the media stream. All right. So they go through a couple of scenarios here, matchy scenarios, and they say, okay, let's go ahead and match the scenario with the result of the call. So Phone A supports codecs AACLD, G711, G729. Phone B supports G711, G729. The region calls for 729. The call will obviously proceed with G729 in that particular case. Phone A supports AACLD, G711, G729. Phone B supports 711. Obviously, the call is going to proceed with the 711 codec. Phone A supports AACLD, G711, G729. Phone B only supports G711. The region calls for G729. There is no transcoder. The call is going to fail in that particular case. And then the last one, Phone A supports AACLD, G711, and G729. Phone B only supports G711, but we do have a transcoder available. The call is going to proceed, and the transcoding will have to take place. Now, where that transcoding will take place, at which point in the network it'll take place, will really just depend on where the transcoding resources are defined, and so on. All right? All right. So the next section we're going to talk about is basically just the call setup process and call teardown process, depending on the type of phone we have, depending on the type of device we have. There are actually, like you've already seen in our discussion, different ways or different types of protocols that we can use as a call control protocol. But generally, fundamentally, most of these protocols have similar steps when it comes to actually setting up and tearing down the call. And this diagram kind of depicts that particular process. Now, keep in mind that this defines call routing between phones that are registered to different call agents. So, you know, you could certainly see something different if you had two phones that are registered to the same call agent, but it's basically the same process. So the first thing is the initiator goes off hook. They lift the handset. That means that we go off hook. They're going to receive dial tone in their earpiece, and they're going to dial the called party number. All right. Those digits can be processed in one of two ways. They can either be processed digit by digit, or they can be processed in what we call N-block, EN-BLOC. N-block mode means we're processing the number as a whole. Now, later on, we're going to get into the call control protocols, and we'll talk specifically about how SIP or skinny or even different types of SIP, depending on the type of phone or the SIP implementation, will handle calls, because it's not really specifically, we don't say that SIP always uses N block and Skinny always uses digit by digit. So we will talk about that when we get into the protocols. But in any event, we're collecting those digits, we're collecting that information, and that becomes the DNIS, the DNIS, the Dialed Number Identification Service, or the called party number. Those digits get sent to the call agent. In our case, of course, it would be Cisco Unified Communications Manager, or it could be a voice gateway, but it's some device that's going to actually take that call. We also have Endpoint Discovery. That call control agent needs to now be able to identify where that call is supposed to be routed. It could be a locally registered directory number on a locally registered device, or it could be a pattern that we're dialing that goes to a trunk, a PSTN trunk, or a ITSP SIP trunk, or something like that. So we have to do our call treatment. We may do some sort of digit manipulation, number expansion, dropping an access code, a globalization of the numbers themselves or whatever for the call to route. But then we also have to check the permissions. Does the appropriate search space exist on the dialing phone in order for them to be able to dial those particular digits? We'll also go through some sort of bandwidth check to see if there is any kind of call admission control implemented. Call admission control allows us to identify whether or not a call can proceed based on the amount of available bandwidth. And there are two primary ways of handling call admission control within the UC environment. You can do localized call admission control, where you're using regions and locations, or you can use gatekeeper controlled call admission control, where you're actually using a gatekeeper and different signaling to identify whether or not a call can proceed or not. But let's assume that the call can proceed. Then we're going to get the call progress tones. We're going to send the ringback tone to the user. That's what you hear in your ear as the call is proceeding. And then the called party is going to be engaged. They're going to get the call displayed on their display, and they're going to get the ringing on their display as part of the call setup. All right, so that's the first part of the process. Once the call gets answered, now we have to establish how we're going to communicate. You'll notice here that call detailed records get logged. A call detailed record identifies the parties that are participating in the call, the date stamp and the time stamp for that particular call, and so on. That call gets logged. Assuming that call detailed records are being recorded, you can turn that feature off on Call Manager if you want to. But the calls will be recorded. The information about the call will be recorded, including, if it's an IP to IP call, meaning we're terminating the call on 2 IP endpoints. All of the characteristics of that call, the RTP ports that are being used or negotiated, the control protocol, and so on. So the call gets answered. The call progress tones are no longer necessary. So we're going to get a message back to the originating phone saying, hey, stop playing the ring back and let's go ahead and start negotiating the parameters of the call. This is where we do our capabilities exchange. We do our codec negotiation between the two endpoints, so we can identify what codec that we're going to use for that particular call. All right, assuming that we have a common codec that's supported, the call is then going to proceed to setting up the media stream. So that's what I was talking about previously when I was talking about the lack of transcoding resources. Transcoding would only be required to establish the RTP media stream. All of these other events that we just discussed take place before that would have to happen. Even though the call may be set up, the call progress can proceed, we may fail at this point if we don't have a common codec between the endpoints and we don't have any common or a transcoding resource that's available. We negotiate the RTP streams. Of course, we talked quite a bit about RTP in the last discussion. RTP is the Media Transport Protocol. It uses ports UDP ports 16384 to 32768. I mentioned 32768 because of the even numbers, or 32766, I should say, because 32768 wouldn't be possible. But we use the even port numbers in that range. rtcp, we talked about that protocol as well to provide us information about the stream itself. That's going to be using whatever RTP port number is being used in the direction plus 1. So it's the odd numbered ports. But you'll notice that we have 4 separate communication channels that are being created here, which is a really important concept if you think about it. It is entirely possible, although unlikely, but entirely possible that you could have one-way audio. If for some reason those UDP ports are being blocked in one direction or being misrouted in one direction, but they're not being blocked or misrouted in the other direction. So typically if you have a one-way audio problem, you need to investigate how RTP is being routed if you have asymmetric routing, and if you do have asymmetric routing, what falls within those asymmetric paths that could potentially be blocking that media stream. All right. If I hang up the call, pretty basic process. I go through the same process. That's called going on hook. We're going to go ahead and record that the call was hung up. We're going to send a closed connection message to the other call agent or the other device that's responsible for terminating the call on the destination extension. We're going to release the bandwidth, and we're going to acknowledge that particular process. So this is a very, very generic way of looking at how a call is going to proceed. Now, obviously, if we're talking about specific protocols like SIP or Skinny or H323, there are going to be different types of messages and transactional events that occur between those protocols that are unique to those particular protocols. We'll get into that in a little bit more detail later on. All right. How does rtcp determine which port to use? It randomly selects a port between 16384 and 32768. No, that's not true. It selects any even numbered port. That would be the correct answer. And actually, that's a little bit misleading, right? Because it says it selects any even numbered port, but it doesn't technically select any even numbered port.
Is the highest even number?
Well, you know what? I misread the question, so I apologize. It's going to do them consecutively for RTP in the order that the numbers are listed. But here they're saying, how does rtcp determine which port to use? rtcp uses whatever RTP port is being used plus 1. So that makes a little bit more sense because, yeah, to say any even number, any odd number port would indicate that it could be the entire range of 65,000 ports. So I just misread the question. I apologize. All right. But we know that RTCP does use the next port based on whatever RTP used in its configuration. So now let's take a look at the SIP calling and setup and teardown for a SIP call. Again, like I mentioned before, we could use Skinny. Cisco tends to talk less about Skinny, even though it is technically their protocol. They talk a little bit less about Skinny because it's kind of being phased out. But what you're seeing in this diagram is the call setup and teardown between two different SIP gateways. Now, we're assuming that SIP is running end-to-end. It doesn't necessarily have to run end-to-end. The phones themselves could be running Skinny, and then we could have some sort of SIP trunk that's configured between the two CM servers in this particular case. But in this case, we're running SIP end-to-end. So same basic process. We initiate the call on the left. I talked about what a user agent client and a user agent server is when I talked about the SIP protocol. Remember, all of these devices are running both functions. That's required with SIP. So the user agent client sends an invite message to the user agent server of the recipient. All right. Now notice that that invite gets passed through Cisco UCM and over to the UCM server on the right. Now that doesn't mean that the UCM server on the left isn't involved in that particular process, because again, we still have to identify whether or not that phone number is we're even able to dial that phone number based on our class of restriction or class of service, and whether or not that destination is identified and the destination pattern that I'm trying to dial is actually registered. All right. The UAS, which is the right CUCM server, responds to the invite message basically with that 100. Remember, 1XX is, okay, I've received a valid message and I'm in the process of progressing and proceeding with your request. So I'm going to send you a 100 message back saying I'm trying to establish the call. That terminating gateway, in this case the call manager, sends a ringing signal to the recipient's phone, and then the recipient's UAS, again, the UAS and UAC don't always assume that call manager is the server and the phone is the client. Both devices are running both functions. All right, we're going to tell the UAC about that ring signal. And we're gonna, with a 180 ringing message, just again another, that's kind of the ring back message, indicating that, hey, we're progressing. You know, again, the 100 messages are generally good messages, meaning that we're kind of progressing through the process. You don't need to know the specific codes for the exam. There may be some SIP traces. Cisco loves to do that, which is kind of annoying, where you have to actually go in and look at a SIP trace and see what's happening based on the SIP trace. But generally, the answers in that case are, you know, the call is proceeding or the call is failing. So you have to have a general knowledge of what those codes represent, maybe not necessarily the specific code itself. All right. So we send the ringback tone to the original caller. That's step number 6. The called phone goes off hook, meaning that they answer the call, and we determine the parameters of the call. Again, we're using SDP in this particular case to identify the parameters, the session description protocol, and in this case, where the parameters are okay, so we're going to say, okay, let's go ahead and proceed. That's the 200 OK message. We get our acknowledgement back. At this point, we have all of the information that we need to establish the RTP session. Now, here's a very important concept. The call agents are only involved in setup, teardown, and modification of the call. They are not involved in the media function. All right? And it doesn't matter if it's skinny, if it's SIP, if it's H323. The call agents will not participate in the RTP media stream unless you're doing things like conferencing, you're streaming music on hold or something like that, unless the call manager is actually having to participate in terminating that particular call, the media stream. So basically at this point, the devices establish their RTP sessions directly between them. All right, so I know it says the RTP stream is kind of terminated between CUCM on the left and CUCM on the right. That's actually not true. Now, it would be true if that's a trunk between them, okay? And in this case, I think that's what they're depicting, that there's actually a SIP trunk between the call manager on the left and the call manager on the right. And in that case, the call would be terminated between those two endpoints. But let's say it's two SIP phones that are registered to the same call manager. Those two endpoints would communicate RTP directly with each other. We would not have to send the RTP through the call manager. So there's a diagram that I typically use to kind of describe this relationship. I have this circle that basically describes the process. I've got a phone on the left, I've got a phone on the right, and then I've got my call agent at the top here. All of the control messages go from here to here, right? So those are my SIP messages, but the RTP goes from there to there, and then we also have the corresponding rtcp from there to there. So, and it doesn't matter if this is a gateway or if it's a phone. It doesn't matter if this is a gateway or a phone. The endpoints will always communicate directly to each other. So you could actually shut down this box and that communication as long as the function of the call doesn't change. You know, somebody doesn't put the call on hold or terminate the call or whatever. That call will still proceed even if the call agent isn't part of the process or isn't available. All right. So that's an important concept. In this particular case, they're not really describing that. They're saying, okay, that call is between the two UCMs, but that would make sense if there's a trunk between them. All right. Only if one of the participants terminates the call, then we're going to get a bye message, and then that bye message is going to be acknowledged. All right. Now they do mention, finally here, the SDP information. I did talk about SDP. SDP is not used to deliver media. Of course, RTP is used to deliver the media, but SDP is used to negotiate the function of the call, the session information. SDP is specific to SIP, by the way. You're not going to see SDP with skinny phones. Call manager is the one that kind of interprets and negotiates all of the communication between the endpoints in a skinny communication. All right. So this particular diagram represents two examples of SDP. The table kind of explains the different parameters that are being used. So there's the version of the protocol. I kind of started going through this a little bit, and I thought, well, if you can't really see it visually, it doesn't make a whole lot of sense to describe it. But the version of the protocol, the origin is who's originating the call, right? The sender of the message, and it includes things like the username, the address type, the address value, the session ID, and so on. Then we have time. So these are our timestamps. These are not, actually timestamps are not going to be seen in the call setup, but they do get set once the call proceeds. All right. And then we have the connection data. And this is what Cisco loves to test on the exam, being able to interpret the connection data. So you see in the example on the top, we have M equals audio 49100 RTP AVP 0. All right, so that means that we're using port 49100 and we're using G711 MULAW. MULAW is the companding method. We use MULAW in the United States of America and in Japan, and the rest of the world uses ALAW. It just happens to deal with how the transcoding, how the quantization process and encoding process takes place. In the second example, we can see 3456. Again, that's the port number, RTP AVP 1808. So 0 is G711 MULAW, 8 is G711 ALAW, and 18 is G729. So we're actually indicating in the video or the audio and video profile that we support 3 different codecs, right? And in this case, it's 18, 0, and 8. All right. Now, the list is actually ordered in priority. So 18 would be preferred in this particular case, but those are the codecs that are defined in the audio-video profile. And unfortunately, you do have to memorize them. They do like to ask about them on the exam. 0 is certainly easy to remember because 711 MULAW is what we typically run in the LAN, right? So I would say at a minimum, know 0 and 18, but you know, the dynamic ones might be important as well. Okay. All right. All right, let's go ahead and get into discovery number 3, configuring and troubleshooting collaboration endpoints. Call Manager supports a lot of different endpoints, desk phones, video endpoints, software-based endpoints, third-party endpoints, and so on. We can actually implement SIP or SCCP. Those are kind of our two main line-side signaling protocols that are supported by pretty much every, well, actually every call manager platform. All endpoints support usually both of these protocols. Some of the newer endpoints might be SIP only, but for the most part, most of our endpoints are going to support both of those protocols. The features that are supported in those protocols is similar. The way that the signaling takes place, the way the devices communicate with each other is obviously going to be different, and we talked a little bit about that when we described the call setup and teardown process and the SIP call signaling process and skinny process as well. All right. But the choice of the protocol really is, well, I wouldn't necessarily say it's a personal preference in deployment. There are certainly some benefits to running SIP as an open standard protocol as opposed to skinny, and then you're going to get some additional features with SIP. But the SIP protocol is kind of the de facto protocol moving forward for most of our modern Cisco endpoints. So in this discovery, we're going to register IP Communicator with our HQCUCM box here, we're going to use SIP in that particular case, and that's located in our San Jose site. All right. CIPC1 is going to be already pre-configured. Sorry, this one right here, already pre-configured on the CUCM server. We're going to go ahead and add CIPC2 to HQ, and we're going to register that to the call manager. We're also going to go through the process of troubleshooting the registration issues between IP Communicator and CUCM, Unified Communications Manager, in a different cluster that's actually located in RTP, Research Triangle Park. For this purpose, we're going to use our Site 1 UCM, which is pre-configured to support only specific registration issues. We're going to troubleshoot the registration issues for CIPC3 and CIPC4 as they try to register to that particular call manager. All right, so we have, like I said, 4 PCs. Each of those PCs are running our CIPC application. The ones on the left are going to be in the 10.1.5 subnet. The ones on the right are going to be in various subnets. We got one in 10.1.99 and one in 10.1.35. All right, so the first thing that we want to do is we want to analyze the Wireshark capture of a SIP call setup and teardown process. So we're going to actually open up a Wireshark capture that was taken during essentially all of the different phases of a call setup using SIP as the protocol between call manager and the 2 Cisco IP communicators. So let's go ahead and go into PC number 1, and we'll go ahead and log in here. Let me click on the window there, C0LL@B. Why isn't it typing? Hold on one second. C. That's weird. Couldn't get into that window there, but let's go ahead and open up a browser, and we're going to go over and browse to the files that were actually created during this Wireshark capture. We're going to go to 10.1.5.100, which is basically servicing these files for us, 10.1.5.100. And we're going to load up our Wireshark captures. All right. That's strange. It's taking a little while to refresh here. Not sure why. All right, but here's our Wireshark capture right here. And the first thing that we're going to look at is the SIP call setup and teardown Pcapp. That's the last one here. We're going to go ahead and save that, and then we're going to open it with our Wireshark application. All right. So let's go ahead and double click that. It should open up in our Wireshark application. All right, in the edit bar at the top of the Wireshark application, we're going to do a little bit of a filter because we have lots of information that's actually captured in this Wireshark, and I'm going to put the filter of TCP port equals 5060 because I want to look at the SIP protocol information as well. So this command basically allows us to filter all the traffic that was captured to only show the traffic that was using port TCP 5060, which is the port that SIP uses. We're going to go ahead and select the first invite message. So let's go to our first invite message. And one of the things we want to notice here is what is the destination port. The destination port is 5060. And which frame is the first invite frame? Well, if we're looking back at the list here, the first invite frame is 902, right? We've got a notify and an OK indicating that that message was received, another notify and an OK, finally a TCP acknowledgement, and then we see our first invite. All right, so 902 is the first invite. The IP communicator is actually signaling this call. We can tell who's actually originating this particular call based on the source address of the packet. In this case, it's 10.1.5.200, which happens to be the IP communicator application for CIPC1. And what type of call setup is this call? And if we go back and look at 902 in the list here, we can actually see that. Going back to packet 902, we see a SIP invite. We can see that it is a request packet. All right, so it's a SIP SDP request packet. We talked about this in our lecture portion. This means that this is an early offer packet because it actually includes session information, the SDP information. We have delayed offer and early offer. Delayed offer would not include any of that SDP information, whereas the early offer does. We can also tell what telephone number has been dialed based on the SIP URI 11002 at 10.1.10.1.55, which is our a SIP server. So we're identifying that endpoint 11002. And then in the packet itself, if I go into the packet and specifically look at the message body information, I can actually see in the session, in the SIP invite message, there's a component called the message body. And in that message body, I'll actually be able to see the SDP information that's important for identifying how this call is going to proceed, all of the capabilities of the endpoint, and all the different details for that particular endpoint. All right, so we're seeing all of the SDP information. Which codecs have been offered in the SDP message? All right, well, if I go into the media description field, I can see 0, 8, 18, 116, and 101. And we can see that information right here. Hold on, let me get rid of that. There we go. We can see that information right there. In addition, we can see all the different media formats that are supported in this particular case. So we got G711 PCMU, G711 PCMA, and G729, as well as dynamic RTP type 116 and dynamic RTP type 101. So specifically in this case, we're talking about G711 ULAW, which is the PCMU, and G711 ALAW, which is the PCMA, as well as the G729 codec. All right. All right. So, this is the information that's important if you're trying to troubleshoot compatibility issues between endpoints, you're trying to identify any particular issues, or even just how the devices are negotiating that session discovery information. That's an important concept. All right. So if we want to identify which options are identifying the reason that we actually see 2 invite messages. If I go back here, I can actually see, and I saw it earlier, I see 2 invite messages, one with trying, and then finally we get our acknowledgement. We see those 2 invite messages, frame 902 and 914, and we have to kind of look at the differences between those 2 messages, right? Clearly we can see that there's a bit of a difference here, right? We're seeing, especially in the SIP URI, 11002 at 10115, so we're seeing that message, and then we're also seeing the information that's coming from Call Manager, Unified Communications Manager, and going back to the phone. We can actually see that right here in this first invite. If you look at the IP addresses, 10.15.200 to 10.115 is one of them. And then if you look at the other one, the other invite, it's actually from 10.115 to 10.15200, as opposed to being from 10.15200 going to 10.115. So one is a reply, in essence, packet 914 or frame 914 in this particular case is a reply to the initial invite message. All right, and we can also actually tell which Cisco IPC on the PC1 or when the Cisco IPC on PC1 begins to ring back, because we can actually see the ringing message as well. So we're seeing all these different transactions that are taking place to allow us to identify the progression of the SIP conversation in this particular case. We can also identify in the SDP information, in the SIP information, what extension John Doe has. So let me go ahead and go back into the packet here. Let's see, we should see it in all of these, but let me go ahead and delete that markup there. If I go into the packet, where's my invite, my initial invite right here, I should see in the SIP information, if I get past the TCP information, I should see information about the user. I may have to actually go into, that's the SDP information. Here's the request, and here's the SIP URI. Let me go back to the ringing one, and let's see if we see that information there. We should see in one of these packets information about the specific end user right here. So John Doe has an extension of 11.0.0.1. So we can see that information right here. Okay, so that's very helpful as well. We just have to look at the appropriate packet type to be able to see that information. All right, what codec was actually chosen for the call can be identified as well. We have to actually go and look at the acknowledgement, and that's going to be kind of further down the line here. We have a whole bunch of different packets that are being sent back and forth. But if I look at specifically 2104 here, I can come into 2104 and I'll be able to see the actual payload that was selected based on the media description. All right, so that's the active time. Let's see, media attribute. It should be right after the time description. So let's go into this section here, and sure enough, we can see from right there that the media format that was chosen was G711 ULAW in this particular case. All right, we can actually even see the port number that was chosen, 27036. Remember, RTP uses even numbered port numbers, and the rtcp counterpart would use the next possible rtcp port number. All right, now if we go look at the teardown process, we kind of scroll down here, and let's go down to, let me see, looks like right about here. Yeah, there's our first bye message. All right, this indicates who's actually ending the call. And we can see that the 11.0.0.1, and which is actually 10.1.5.201. We can see that based on the source address here. This is the one that's actually initiating because that's the source. This is the destination, and we're saying let's go ahead and terminate the call, and then we have our acknowledgement in return. All right, we see the two by messages because one was from one endpoint. Let's take a look. Let me clear this off. We see this by message here, and then we see in 4560 another by message. So the one was from 4559 was from the CIPC agent phone or CIPC user phone, and the 4560, this one right here, is from call manager. Okay, so this is an example of kind of how we can capture the SIP transactional information that's going back and forth between the endpoints using Wireshark, and then based on that information we're able to easily identify what's happening in those transactions, who's initiating the call. If there were some issues, if we all saw other messages besides 1XX messages or 2XX messages, we could then go and analyze those 4XX or 5XX or 6XX messages to see what kind of problems are having or occurring between the endpoints. So we're going to move on to task number 2. In this task, we're going to configure and troubleshoot a collaboration endpoint. We're actually going to register CIPC1 with our HQ UCM. We're going to configure CIPC2 with the phone itself and the directory number in the HQ UCM server, and then we're going to register CIPC2, that CIPC2 phone with the UCM at the San Jose site. And then we're going to go through and finish up this section by troubleshooting CIPC, CIPC3 and CIPC4 at that Site 1 UCM server at the RTP site. So in order for us to achieve endpoint registration, we have to configure Cisco endpoints with different operating parameters before we can actually use them or even make and receive calls or run different applications. That configuration has to be performed in advance on the call processing server or a call manager, or if we're using like an ISR router on the ISR router. All right. Now, once that device is configured, we can generate a configuration file. We talked about that configuration file specifically being the Cnf.xml file that gets generated. That's going to get stored on our TFTP server, and then the endpoints can go through their boot up process. They can go through the boot up sequence. They can retrieve that configuration file before they register to the server itself, and then they're ready to be used. So we're going to register CIPC1 and we're going to register CIPC2 with our HQ UCM. We'll take a look at the status of IP Communicator and move on from there. So let's go to PC1. Well, we're already in PC1 here. We're going to go ahead and open up Chrome, and we're going to use Chrome to access our Unified Communications Manager. So 10.1.5.5, oops, 10.1.5.5, and we'll log in. That's our self-signed certificate. We saw that before in one of our previous discoveries. And let's go ahead and put in our authentication credentials. Administrator and C0LL@B. All right. So the first thing we're going to do is go to Device, and we're going to go to Phone, and then we're going to click Find to see if we can find our phones. All right, Device, Phone, and let's see what phones are already currently registered to Call Manager. So we can see CIPC1 is configured, but the status is listed as none. And we can also see that there's no reported IPv4 address listed here. So let's go ahead and take a look at the configuration of that phone. first of all, we'll just kind of click into the phone here. That's the name that we're going to have to ensure that IP Communicator has configured on it. All right. Let's see, why is it not selecting it? There we go. Turn my mouse here. All right, and we can also see from this configuration, we do have a directory number configured on the phone. It's 11001, which is not really a problem. 11001 is not in a partition, but typically we would put those lines into a partition. All right, especially if we have class of service configured. So the first thing I would probably want to do is, probably put that into a partition, most likely the line internal partition. Let's see if that partition is actually identified. So we'll click on the line itself, and let's see if we put that into the line internal partition. We'll go ahead and save that. And then we'll do a reset, save that, and then we'll do a reset. We'll just do a soft reset on that. All right, now the next step is to go into our IP communicator, and we're going to have to set up the properties of IP communicator. So let's open up our IP communicator application. And we want to go ahead and make sure that the device name matches on IP communicator. We don't have to do this on a physical phone, but on these soft phones, we have to identify the name of the device based on what's configured in Unified Communications Manager. So the device name is CIPC-1, and the TFTP server is already set correctly. All right, now IP communicator is going to reset because the protocol is already set to SCCP by default. We've provisioned the phone as a SIP phone within Unified Communications Manager, a SIP CIPC phone. So as soon as I save this configuration, the phone is going to reboot, and we might actually see it reboot a couple of different times as it downloads the new software and goes through the process of upgrading itself, or at least changing itself to a SIP phone. All right, there's that process of downloading CIPC locale.zip for the locale information, as well as the phone information. And it might actually boot a couple of different times. Phone is resetting. The extension is showing up. It's going to reboot one more time. And finally, we should see it show up on the display. Now, when we go back to Call Manager, if we go back to our Call Manager application, and we go back to Device and Phone, let's just go back to the device here and go back to our list. We should see that phone now shows as registered, and we can see the IP address of 10.1.5.200, which, by the way, is just the it's just the IP address of the PC that CIPC happens to be connected to. So now our next task is to go ahead and add that second phone. It's going to be IP communicator number 2. We're going to configure it as SIP, and it's going to have a device name of CIPC2. The device pool is going to be HQ. Pretty much the same information that we have on CIPC1, although in this case we're going to assign this phone to user J. White in this particular case. So we're going to add a new phone. We're going to go ahead and select a Cisco IP communicator. You see all the list of the different phones that are available in this system here. We have quite a few phones obviously available. Lots of different endpoints, but there's our Cisco IP communicator. We're going to go ahead and click Next, and we're going to provision this as a SIP endpoint. All right. Again, it'll still function as a skinny endpoint, but we like to kind of standardize on SIP in most cases. All right, let's go ahead and give it the name. Again, the name has to match what is, sorry, this is going to be number 2, what is configured on the soft phone client itself. CIPC phone 2, phone number 2, the HQ is going to be the device pool. We're going to just make this a standard CIPC phone, standard CIPC user, find that in the list. The phone button templates are a way for you to kind of customize the appearance of the phone itself and how the buttons are going to be provisioned. We're just going to use the standard one, and then the location is going to be HQ. This is for the ability to identify the locale of the phone, the location of the phone, excuse me, so that we can use that as record resources and also for things like call emission control and so on. J White is going to be our user in this particular case. All right, so the user is going to be J White. And that should be pretty much it. We do need to define the SIP, device security profile, and the SIP profile. Those are required configuration elements that do not default to anything. We can see here the SIP profile is set to none. We're going to use a HQ SIP profile that we had previously configured, and the device security profile is going to be set to non-secure, standard SIP, non-secure SIP profile. All right, we'll get into those discussions a little bit later on as to why we would have to have those particular settings. So let's go ahead and save that configuration, and that should populate that phone, and now we can go ahead and add the directory number to the phone. The directory number's already been provisioned. It's going to be 11002, and we're going to go ahead and put that into the internal partition. Everything else is pretty much going to get populated. We may want to move these back to, I'm not sure how the search space is set up. In fact, let's go ahead and do that. Let's leave it in the none partition right now, just for now, because I'm not sure how the search spaces are. Well, we actually haven't assigned any search spaces to these phones presently. So we would want that to be in the none partition. We'll have to do the same thing back on that other phone that I changed previously. All right, one more thing that we want to set is the display caller ID. So, you know, what will show up when this person calls somebody else. And also the ASCII display caller ID information. And then finally the line text label, which will show up next to her line button, the first line button that we assign the extension to. This is the label that's going to show up on that line button. All right. As you can see, there's a whole bunch of other things you can configure here. Obviously, we're not doing everything at this point. We're just doing our basic provisioning, and we'll go ahead and save that device. Now, before I forget, let me go back up, go back to my list of phones. And I want to go back to CIPC1, and for some reason my touch screen's not working with that button there. And I want to modify this line configuration. Let's go ahead and put that to none for now, because again, I don't believe in this particular discovery that any of the calling search space or class of service functions have been actually configured. So now we're going to go into CIPC or computer 2, PC number 2, so that we can now configure and set up this IP communicator. All right, so let's get into this. I don't know why I have such a hard time being able to click on this window. It's really strange. All right. We're going to launch IP communicator on this PC as well. And we need to go in and provision this one, just like we provisioned the other endpoint. Right? We need to make sure it's going to switch from skinny to SIP. We have to make sure it has the appropriate TFTP information and the appropriate device name information. We could provision it with the SCP MAC address information if we wanted to, but oftentimes it's a little bit easier to kind of identify these types of phones if they've been provisioned using the custom name basically that we want to apply. All right, so the phone is booted up. I should be able to now dial 11001. That call should ring through, and let's see, it doesn't look like it's actually dialing. Let me scroll down here a little bit. Well, 11001 would be a better number to dial. All right. And let's go to the other PC and see if that call is actually ringing through. Scroll, minimize this. So it doesn't look like the call's actually ringing through. Let me try the other direction, 11002. That one's ringing out. Okay. Yeah, we can see the call coming in. So let me answer that call. We don't have any audio in this case, but we can definitely see the calls coming through. So let's try this again, 11001. And we should see a ring out. That's interesting. We're not seeing a ring out in this case, but I'm not sure why that's the case, but we're definitely getting the call in the other direction. All right, we can troubleshoot that actually. We can go take a look at our Unified Communications Manager. Let's go back to PC1, go back to our call manager, and see why, for some reason, we're not able to ring that extension. We did change the partition. We need to save that, so that's probably why it didn't save. So that's why the call didn't go through previously. I forgot to put the save button there. We'll go ahead and go back to the device and we'll reset the device as well. We're getting some delayed audio for some reason from those calls that I placed earlier. It's interesting. We're using Cisco's actual labs, and I don't know where these labs are located, but the audio is having some issues. But we can still basically see the basic functionality. I'm going to reset this phone and close that, and then I should be able to go back to PC number 2 now and dial that number. So let's go ahead and seize the line, 11001, and we can see the ring out. So we know that the call is proceeding in this particular case. So the call proceeded, no problem in that particular case. All right. So, you know, pretty basic setup. I mean, we really just kind of added the phones and made sure that they had the right appropriate configurations. Normally, I would also try to configure a restrictive dial plan for these users, you know, put the phones or the lines at least into a calling search space. And then based on that calling search space, you know, we're able to apply class of restriction to that particular device. All right, so our next task is going to be to troubleshoot Cisco IP Communicator. But in this case, we're going to troubleshoot CIPC3 and CIPC4. These devices are registering to our Site 1 UCM at the RTP site. So let's go into PC number 3, and we're going to go ahead and log in and launch IP Communicator and see what happens with this IP Communicator application. All right. So we're going to launch IP Communicator. We can check the configurations of IP Communicator as well, but we're going to let it boot up and attempt to register. We're going to see in this particular case, well, let's make sure that we have the appropriate settings first once the device boots up. This one is called CIPC3, and it actually should point to server 10.1.15.5. So let me right click, go into my preferences. Let's make sure this one has the name of CIPC-3. And we want to make sure that the TFTP server is set to 10.1.15.5. All right, those are we know that those are going to be the correct settings. But the phone is going to try to reboot. We know it's not going to work. That's kind of the purpose of this particular exercise, right? It's going to try to register to call manager, and it's basically going to get stuck in a registration status. Now, while that's going, let's talk about the boot up process. It's really important in order for you to understand how to troubleshoot a device, to understand how that device is going to register. When the device is connected to a switch, which most physical phones are going to be connected, if the endpoint isn't plugged into a device that is going to provide power over Ethernet, or it doesn't have a power cube connected, the device is going to make an attempt to communicate to the switch that it needs power. All right, and then the switch is going to apply the appropriate amount of power based on the type of device. If for some reason there are not enough power resources. Now, obviously, in the case of IP Communicator, we're not doing power over Ethernet because it's just a soft phone on a PC. But once a physical device gets its power, if the device security is enabled, the endpoint is going to provide its credentials to the security server over that infrastructure. And if it is actually allowed to use the network, the endpoint is going to get all of its parameters, things like IP address, DNS server, gateway address, either through some sort of static provisioning or but most likely through DHCP. In that process, we're going to obtain a TFTP server IP address as well through the static provisioning process or through DHCP option 66 or DHCP 150. Because this is IP Communicator, we do have to configure the TFTP server and IP address manually. The TFTP server IP address manually because option 150 is not going to be passed through the device because the PC is not going to request option 150 in this particular case. We use that TFTP IP address then to get our Cnf.xml file, either the default or the specific one for the device, and then we register to the endpoint. Now, if I go in here and I hit the settings button on this device, and then I go to status messages, let's go to status first, and then we'll go to our status messages. We can see a TFTP timeout error, right? And it's actually looking for, well, we need to change the settings here. Hold on one second. It doesn't look like the settings took place because I should be seeing the CIPC-3.cnf.xml since that's the name it should be looking for. That's actually a good thing to note. We didn't see that, which means that for some reason this didn't take effect. I'm not sure why. We should be seeing the CIPC-3.cnf.xml request because that's what we used for the device name in this particular case. So we did set it correctly. Let me go ahead and go back to the settings and the status and status messages, and let's see if we see that here. Oh, there we go. Now it's at the top there, CIPC-3.cnf.xml. All right. The IP communicator is actually configured with the wrong TFTP address in this particular case. Well, it could be. That could be one of the problems, right? We did change it. Maybe we changed it from one that was correct to one that was invalid. It could also be if TFTP is not responding, if we're getting a TFTP timeout, that TFTP service is not running, or there's some sort of connectivity problem to TFTP from this, wherever this PC is installed. All right, so let's go back to our settings button, and we're going to go to our device configuration, and we're going to see the CM1 TFTP server set to 10.1.5.15, and the second should be an SRST reference, in this case 10.1.5.254. Which is not correct either, but in this case it doesn't really matter. But we can definitely see that information. So the first thing I want to do is I want to make sure that the TFTP service is running on Unified Communications Manager. So let's go to our call manager server in this cluster here, and let's log in and take a look under Serviceability and see if that TFTP service is running on this server. So it's 10.1.15.5, which happens to be, by the way, the correct TFTP IP address for this client. All right, we'll go into our call manager portal. Oops, I don't want to go to self-care. Let's go back and go into call manager. We have a self-signed certificate on this device as well, so we'll have to accept that and proceed. And then we'll go ahead and go to our serviceability page because that's where our feature and network services run. We'll log in and COLL@B. And we need to go back and check our feature services. Remember, there are two different types of services that exist within Unified Communications Manager. There are feature services, and then there are network services. The network services are mandatory services. The feature services are optional services that we can run in Unified Communications Manager, like TFTP, like DHCP monitor, even call manager service, right? We don't necessarily have to even run call manager service. So there's our publisher. And if we scroll down here, sure enough, we see that the TFTP application or the TFTP service is not activated. All right. So let's go up here and we're going to go into service activation and activate this service specifically. We can restart and stop services from here, but only after they're activated initially. All right, so we'll go down here to our service activation, go to TFTP, check that service, and then we're going to go ahead and go to the bottom of the page. Let's see, got a couple of different scroll bars here. Hold on. Should be able to get down there. There we go. Save. All right, I guess I could hit save at the top too, but once we save it, whatever service is checked should activate, and we can go back and check that and verify that as part of the process here. Okay. Once we've activated the service, it does take a little bit of time for it to be activated. It also depends on how many other things are running on that platform at the time. Will determine, how long that service is going to take to activate. But now if I go to Tools and I go to my feature services in my control center, I should be able to see that the TFTP service is now active. All right, let's scroll down and we see that TFTP is now activated. So we'll minimize that. We're going to go, well, we don't even have to restart. Well, that's PC2. Let's go back to here. We're going to minimize our browser. And we're going to exit that. We're going to go ahead and reset this phone by hitting the settings button. And we're going to hit *******. That is the soft reset sequence of buttons that you have to press to reboot a device. All right. So we should see the device reboot. You can also kill the device and kind of boot it up again if you want to do it that way. All right. So we can see the device is downloading files, and it's doing that for the purpose of migrating from a SIP device to, a skinny device to a SIP device. It should reboot again here and pop back up. We got a little bit of a bandwidth issue here. It's a little bit slow. I don't know, did I close it? Did it crash? Yeah, it looks like we might have an issue. Oh, we somehow moved. There we go. It's just booting up. I got to be a little patient because we're actually accessing these labs remotely over a VPN connection, so it's a little bit slow, but the phone should boot up, but we're still going to have an issue. I happen to know that because there are some other things that we're going to have to troubleshoot as part of this process. Okay. So we see the device is restarting. It's configuring the call manager list. It's trying to register, and it kind of keeps going through this process. So if I go to my settings button and I go to the status here and I go to status messages, we can see that there is no trust list installed. All right, meaning the certificate trust list file doesn't exist. The phone is not a secure phone. So we need to go to our service activation. We're not necessarily looking for certificate information. It's actually telling us there's no trust list installed, and CTL update has failed because we're not running this as a secure device. But if we go back to our call manager and we take a look under serviceability, I did see this the last time. This is a pretty important concept, right? Call manager service not running. In order for a CUCM server to act as a call agent, that call manager service needs to be running. So we're going to go back up to our service activation and we're going to activate the call manager service. One of the mistakes that a lot of people will make as they're implementing these platforms is they will go through and they will simply activate all of the services on the server because they're not sure which services need to be activated and which services don't need to be activated. It is pretty important to understand what the purpose of each of these services are as you're activating them. You know, because each of these services that do get activated obviously perform different functions, which you may or may not need in your call manager environment, and that's going to take additional resources. All right, we can see the services active. If I go under serviceability for my feature services as well, I should be able to see that call manager service is active there as well. Here we can actually turn on and turn off the services. In the feature services, we have the ability to actually kind of identify that the service is active. We can see call manager started, and I can stop and restart that service, but I can't turn that service on and off in this particular case. All right, now we go back to our call manager, our IP communicator. Oops. I clicked the restart computer button. Hopefully it doesn't restart on me. So I should see this device eventually register. It might have to go through a couple of cycles before it actually registers, or I might have to reboot it. But let's give it a second here to try to re-register. And the phone should register at this point. I'm not patient enough. Let's go ahead and reboot it anyway. Star, star, pound, star, star, exit, and let that phone reboot. All right. Now that phone should register. We should also be able to see that device register in Call Manager. If I go to my Call Manager administration page, and then I go into my devices and phones, I should see that device registered. So device and phone, find my list of phones, and we can actually see CIPC3 is now registered. All right. It literally just registered. Last registered now means it registered within the last, well, very, very quickly. All right. So now we're going to go to PC4. We're going to try and get PC4's phone registered. That's the last PC in this particular group. We're going to log in and do basically the same thing. Launch the computer, check the settings on the device, and make sure it has CIPC4 listed as the device name and the appropriate TFTP server of 10.1.15.5. So we'll go ahead and launch our IP communicator. And again, go through the verification steps. All right, this one's going to be called CIPC4, and we're going to make sure that we have the TFTP server set correctly. So go to Network and change the device name CIPC4. We shouldn't really have any, as long as the phone is provisioned appropriately within Call Manager, we've already verified basically that all of the services are running because the other phone registered. So hopefully this phone will register pretty quickly. All right. Let's see. Actually, we don't have it provisioned in Call Manager. If you go back to the list here, let's go back to PC3. We do have CIPC4 listed here, but notice how it's provisioned. It's provisioned as CIPC4 and not CIPC-4. And we set it up as CIPC-4. So that's going to be an issue. All right, let's go back to our other PC. We should see that the phone is actually not going to register. All right, but let's go ahead and then go to our status and status messages. And what we're seeing here is that it's looking for the XML default.cnf.xml file. That is a good indication that the CIPC-4.cnf.xml file doesn't exist on the TFTP server. And so what it's trying to do is it's trying to basically download a default XML file for that particular device. All right, now if it's a real physical phone, then the device ID would be the MAC address preceded with the SEP, the Celsius Ethernet phone. And we would not want to change that in that particular case because obviously we identify those phones as based on their MAC address. So let's go back to PC3 and let's go ahead and go into CIPC4 and change that provisioning. We're just going to simply change it on the fly. Most of the settings you can change on the fly. Some of the settings actually require you to rebuild the phone. For example, if you want to provision it as a SIP phone or a skinny phone, you actually have to change, or you actually have to delete the phone and re-add it. So CIPC-4, and we'll go ahead and save that. And we'll hit the apply button, apply config. That'll do a soft reset. And then we should see that that phone is now going to register itself. So go back to PC number 4, exit, 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 settings, ***, #**, exit, and the phone should boot up and register. Okay, and we should be able to also place a call from Mary, this is Mary's phone, over to Joe Green's phone, which is extension 12,001. All right, so we'll give it a second to boot up here. Once it's booted up, we'll place that test call, and then we'll be done with this discovery, and we'll go on to our next discovery. All right. All right, the phone rebooted. It's downloading its configuration. It's going to reboot a couple more times, and then it'll boot up with the extension. There we go. Dial 12,001. We should get a ring out to Joe Green, which we do. All right. So that pretty much wraps up this discovery. We're going to get into discovery number 4, troubleshooting calling issues. And then we'll wrap up this lesson by going through a couple of other call control protocol lessons and DTMF lessons and our summary challenge. So we'll see you guys there. All right, let's get into discovery number 4 now, troubleshooting calling issues. Calling issues could involve lots and lots of different things. There's a lot of things that can happen to cause a call to fail. There could be issues with call setup and call teardown process. There could be issues with class of restriction. There could be media resource issues, actually packet routing issues, and so on. So one of the things that we're going to have to become familiar with is how do we identify potentially where those issues exist? What kind of symptoms can we recognize that would give us an indication as to possibly what the issue might be? And then we go through the troubleshooting process. In this particular discovery, we're going to troubleshoot a codec negotiation issue with Call Manager. We're going to use the real-time monitoring tool, what we call Cisco Unified RTMT, to monitor our SDP traces, our Session Description Protocol traces. We have 2 IP communicator phones. One IP communicator phone is located on PC1. That's our CIPC1 phone, and that's going to be located, and the other phone is going to be located on the PSTN. It's our PSTN phone, and then we also have a third phone. We're not using that phone in this case, but we do have a PSTN, a set of PSTN numbers that we should be able to dial as part of our process. All this stuff is pre-configured, and the actual PSTN gateway is already set up to accept register messages from the PSTN phone. CIPC1 is going to be located in our San Jose location. We don't actually have access to the PSTN gateway in this case, but it is already completely configured with all of the dial plan requirements that we have, and so we're going to assume that there are no issues with the PSTN. The PSTN phone can be reached by dialing local numbers from our CIPC1 phone. Those will be our 408, 2 through 9, XX, XXXX patterns, which is our local line. Our national calls, 1, 2 through 9, XX, XXXX. That's our national line. And then our international calls, 011 exclamation on our international line. And then finally we have our emergency line, which has pattern 911. The connection that we have between the HQ site, HQ UCM, and the RTP gateway is actually a SIP trunk. We can see that identified right here, and that's already configured, and we're going to assume that that's working as well. The connection between the San Jose gateway and the PSTN gateway is actually an ISDN circuit path. That's a digital kind of TDM type of circuit path. PC1 is running CIPC1, and that's the 10.15200 device. PC3 is running the IP communicator PSTN phone, which is 10.1.99.101, and our call manager in this case is 10.1.5.5. All right. So the initial configuration of the equipment does actually include a DAO plan. It also has all the pre-configured endpoints. We need to register the endpoints in the San Jose site, and we're also going to have to register the PSTN phone. All right, so PC1 is running CIPC1. That's going to be registered to call manager 10.1.5.5. It's going to have directory number 11,001, and it's going to have a PSTN number of +1 408-555-1001, and it's going to be in the San Jose, California location. PC number 3 is going to be running our PSTN phone. It's going to have going to be communicating with Call Manager Express 10.1.99.252. It doesn't actually have a directory number, but it does have those PSTN numbers that are assigned: the local, the national, the international, and the emergency numbers. And it's going to be located in the PSTN location. So the first thing is, let's go ahead and go to PC number 1, and we're going to authenticate and verify the configuration of IP communicator on this PC. All right, so we'll go ahead and launch our IP communicator application. Pretty much the same thing that we've done on the previous discoveries, just kind of making sure that it has the appropriate device name, making sure that it has the appropriate TFTP server IP address. So we'll go into Preferences, go to Network, set the device name to CIPC-1. It does already have the correct TFTP server IP address, so that device will reboot, and it should register with John at extension 11,001. It might go through the process of kind of converting itself to a SIP device. We'll assume that that's going to go ahead and continue. So let's go over to PC3, and we're going to do the same thing on PC3 for our PSTN phone. All right. This phone is going to have a device name of PSTN, and it's going to go to the 99.252 Call Manager Express box. That represents the the calling agent for this particular phone. All right. All right, right click here, go to Preferences, go to Network. This device name is going to be PSTN. And 10.1.99.252 is actually the TFTP server in this particular case, so we'll go ahead and set that. All right, let's just go back to our other device here, make sure it's registered. John is registered. I would assume that our PSTN device is going to register as well once it connects and reboots. So the next task that we're going to get into is troubleshooting our SDP information. All right. And the SDP information is what we use to establish the capabilities of the call. It's a standard-based protocol that basically identifies all the features of that call. We kind of incorporate, we've seen this and talked about this a couple of different times, incorporate this into the initial SIP negotiation that takes place with either early offer or delayed offer functionality. So in this task, we're basically going to verify and troubleshoot any kind of codec negotiation issues between the endpoints. SIP does use SDP to negotiate the type of media that we're going to use for the session, the audio, the video, the different transport protocols, the RTP and UDP ports that we're going to be using, the media format, right, the audio and video codecs that we're going to be using, as well as other properties. The endpoint that starts the process provides the list of capabilities, although that initial offer is the default. It's the one that has the highest priority, and that's going to be the initial offer, which is our default proposal. The destination endpoint is going to select an offer that matches the capabilities that that endpoint supports, but it is going to keep the list of common capabilities in case we change mid-call or something needs to change during the call. And we're going to need to identify what those common capabilities are. SIP uses the offer answer model. We talked about this in our lecture series to establish the SIP session. The offer is actually contained in those SDP fields that are sent in the body of the SIP message itself. The offer defines the media characteristics that the device supports. What are the media streams? What are the codecs? What are the directional attributes, the IP addresses, the ports, etc. And then the device, like I said, that receives that offer sends an answer in the SDP fields of its own SIP response. That answer is going to include all the corresponding matching media streams and codecs, whether they're being accepted, whether they're not accepted, the IP address, the port number that it wants to receive the media streams on, and so on. All right. So an SDP trace includes that audio traffic that's sent in that SIP invite message. We kind of saw that in our previous discovery from call manager to the gateway. And the preferred codec list includes 0. Now codec 0 is defined as G711 MULA, which is what we use in the United States, and 101, which is our RTP NTP payload support function. All right. So an example of an SDP trace would consist of several different things, like the version, what is the version of the protocol, the origin, that's going to define who's sending the message, and it could include things like username, session ID, address type, address value, and so on. We also have session information, which will allow us to define the session title, connection data, those are the parameters for the media endpoint termination. Network type, in the case of IN, we might see that in our capture. That's going to be defined as internet, and other types can be defined as well based on the RFC. The IP address, whether it's v4 or v6, and the connected IP address as well. We also have a time component, which is represented by T. By the way, the connection data is represented by a C. The time is represented by a T, which defines the session start times and end times, and we'll have those timestamps listed there. The values are not going to be set up initially when the call is set up and signaled, but it will be added as we proceed. And then we have the big section, right? The media descriptors. Those are indicated with a little M character. That's going to specify our media type, our audio and video media types, the UDP transport port that we're going to use, the different media formats. It could be a single media format, or we might be identifying multiple media formats. Different AVP codes that we would see on a regular basis. 0 for G711 MULA, 8 for G711 ALAW, 101 for RTP NTE, and 18 for G729. This is an ordered list according to priority. All right, we did talk about that a little bit when we went into our discussion on SIP call signaling in this particular section here. And then we have our attribute lines. These are going to be represented with the little letter A. Each attribute is going to refer to specific media descriptors. We'll see more of that when we get into our trace a little bit later on. Now the contents of SDP are going to vary depending on at what point you're looking at that SDP information, what kind of endpoints they're trying to communicate to each other, and so on. So we want to go ahead and place a call from CIPC1 to 911. And what I should see in this case is I should see a reorder tone. A reorder tone basically means that the call failed. We're actually getting a ring out in this case. Most likely, we can't hear the audio. We're having the same kind of audio problems we had before. But most likely, we're getting a fast busy, all right? Unfortunately, we can't hear that fast busy. We call that a fast busy or a reorder tone. And it's not being displayed on the phone. Some phones will actually display that. But if I do place the call, and I call 911, we should see that if the call was actually proceeding, it should be ringing on the other phone. All right, and it's possible, well, we are getting a ring out in this case, so that's interesting that the call is actually proceeding. All right, it's actually technically supposed to fail at this point. I'm not sure why it's not failing. The Codec Negotiation is not set up correctly, but we'll go ahead and proceed anyway, and we can see what we see in the RTMT information. The fact that the call went through is not a huge problem. We can go ahead and try some of the other calls as well. Let's see here. Let me go ahead and pause the video, and I want to make a change to the configuration in the call manager for the region so that the call fails. All right, I've gone and fixed the issue, actually broken the, the phone. It was working before, but remember, call setup and call teardown has nothing to do with the media capability exchange. So if I'm placing the call and the call is ringing through, there won't be any problem with that part of it because that is simply part of the call setup and call teardown. The media exchange doesn't occur until the call is actually answered. And we can see as soon as I do that, the call gets dropped and we get a reorder tone. All right, which is what we wanted to see the last time as well. So once we answered the call on the PSTN side, the call is immediately disconnected because we're trying to establish the RTP session now at this point between the two endpoints, and then that's when the codecs are negotiated and so on. So let's go into PC1, and we're going to actually launch the real-time monitoring tool. This is a plugin that you can install from Call Manager, and that should work. Using the name. We might have to put in the IP address, but let's try that. Administrator and C0LL@B. Authenticate. The real-time monitoring tool is a way for us to collect information about the system as a whole. The system summary, CPU and memory utilization, processes that are running on the device. We can look at disk usage, critical services, performance functions, and we can also use the alert central function to grab traces and alerts and so on. All right, we'll let that load up. Sometimes it takes a little bit of time, and especially in this environment that we're using, it might take a little bit of time. We're going to go ahead and use the default configuration list, and you can see all those things that I listed on the left there. All right. Now, in this particular case, we're going to navigate to the voice and video, and we're going to look for specifically, in this particular case, session trace and log information. All right, so let's actually go over here, and let's scroll up. We'll go to voice and video, and we're going to go to session under voice and video summary. We're going to go to session trace log view, and we're going to look at the real-time data. All right, so session trace log view, and we're going to look at the real-time data. Now that should launch the process of collecting that information. Once that collection of data is complete, we can now go look at that call that failed. We'll actually see a couple of calls that went through. I did a couple of tests before I started the video up again just to make sure that it was functioning correctly. So we're going to collect this information, and we're going to specify the amount of data that we're going to filter out, and we'll just filter out the last 60 minutes or so. Just pause the video while the data is being collected. Sometimes it could take upwards of 5 minutes for that data to actually be collected. All right, we've collected the information. We can see the calls. I placed several different calls in this time frame. We don't really have to filter out the information at this point because technically we obviously really don't have a whole lot of information. But I can go ahead and apply and run that filter to collect that information over the last 60 minutes. And it's going to go through and collect that detailed information. And then we're going to take a look at the actual call, and we're going to see the results for that trace for that call. And this will represent as a diagram. We're going to have CIPC1 at 10.1.5.200. That's communicating to 10.155 as the call manager, and then that call is then in turn being sent over to 10.15252. And we should see all of the SIP information, the invite messages, the trying messages, the session progress messages, the ringing messages, the acknowledgments, and then finally the bye message once the service, we get a 503 error indicating that the service is unavailable. All right. So we can basically select any one of these calls in the list here. I'll go ahead and grab this information, and this is the diagram that I was referring to that provides essentially the trace, the SIP trace for the call itself. 10.15200, we can see the invite message and the trying message. If I click on the invite message, I can actually see the SDP information. I can see pretty much like I would have seen had I seen this in Wireshark or some sort of Wireshark capture. Right? We can see that CIPC1 in this particular case, if I scroll down here, is negotiating right here different types of codecs, and we can see those listed right here. M audio, the port number is 32382, 08, 18, 116, and 101. If I go into that flow diagram and I click number 3, let's go back to our flow diagram. Let me turn off my annotation tool here. Go back to my flow diagram and I see invite number 3, and I'm looking for the similar information. In this particular case, this is the message that was sent from call manager to the gateway, and call manager uses a delayed offer. We don't actually see any SDP information in this message at all. We see the contact information, the PSTN contact information, but we don't see any of the SDP information. If we go back to our code flow diagram and click on number 7, actually let's look at the 200 OK message, which in this case is number 8. We can see in this particular case, maybe this is not the right message. Let me go back here. And I should see it in maybe number 7. Let's see here. Nope, not number 7. And actually what we want to go into is we want to see the trying message here, message number 4. This is going to indicate how we're trying to communicate the call. And specifically, I went to the wrong one again, session progress information. We should see here's the SDP information I was looking for. So this is the information about the gateway, basically telling the call manager what it's going to support. And you can see in this particular case, the audio that we're supporting is different than what we saw in the initial setup, right? In this particular case, we're seeing that we only support 0, which is G711 ULAW, and 101, which is RTP NTE. All right. And in the previous example, we saw many more codecs that were supported. If I go to the bye message now, let me scroll down here. We should see the bye message. Where's the bye message? Invite, request canceled. I wonder if it's cut off here. Let me try and go to a different call here. We should see a bye message. I did the calls a few different times, so I have to find the call that actually includes that information that I was looking for. There we go. This is the actual call trace that I wanted to. The other calls I hung up before I answered them, so we didn't see the entire trace. Now we're seeing the trace here. So if I look at the bye message in this particular case, number 9, we can see that this is sent from call manager to the gateway, right? And the question is, why would this happen? What would be the reason that call manager doesn't agree with the gateway? The phone supports G711, so maybe the reason is that there is a region configuration mistake. Of course, we know that's the case because I went and changed that so that the region would not function correctly. And we can see from the SIP trace that the resource is unavailable. So if I go down here and I look at the reason code, which is cause code number 47, we see that right here. Of course, you'd have to be able to discern what that indicates, but 47 means basically that there is no resource with the capabilities that match for us to be able to establish the audio stream in this particular case. So that means that the call is going to get dropped. All right, so now we need to go and fix this particular problem. Let's go into our call manager administration page. Let's close this guy here. We'll just minimize this. We'll go into our call manager administration and we'll take a look at the region configuration. Remember, we're only supporting 711 ULAW on the gateway. So let's see what we have for the region configuration. All right, go to call manager administration, go to system, go to region, and specifically region, and go to HQ. Now we can see from the region configuration that we are supporting the 8K codec, right? That's actually the maximum audio bit rate that we're going to support. And we already saw from the PSTN configuration that we have to support at least G711 ULAW in order for these devices to communicate with each other. Now, granted, we probably would use a 728 codec in this case. That would make sense given that it's a WAN call over the PSTN. But this is just for testing purposes in this particular case. So if we go ahead and change this configuration, we go to HQ, we select the other HQ down here. This is the relationship from HQ to HQ, and we go ahead and specify that we're going to allow that G711 codec, G722 and G711. We'll save that, and then we'll reset and restart the devices that are tied to that configuration, that device pool configuration. Region configuration is actually tied to the device pool. We're also going to now place the call, and we should see the call is going to successfully go through. So let's go ahead and minimize this configuration page. I'm going to go ahead and exit out of the device here. I've had a little bit of an issue with the device doing a soft reset. So I'm just going to exit the device and go back in just to make sure that it's accepting that new region configuration based on its association to the device pool. All right. All right, so let's go ahead and place the call again to 911. And that call should proceed through. Let's go over and actually answer that call and see if the call actually gets connected. And we can see we're on an active call now. So the call is being negotiated correctly. It's being set up. The media streams are being negotiated correctly. And the call is proceeding. All right. Let's go back to our other PC. Let's go back into our real-time monitoring tool and go ahead and rerun this capture. Let's just do for the last 15 minutes. And we should see that call that went through successfully. So I'll pause the video while we're capturing and collecting the information from the database, and then we'll go take a look at that record. All right, we got our traces in here now, so let's go ahead and pull up the trace here. Make sure that this is the right one. This is not the correct one. We want to make sure that we pull up the one that actually went through okay. This is not the right one either. What we should be seeing, I could try and collect it again, but really I'll just kind of describe what we should be seeing here. Let me do the last 75 minutes, and while I'm talking here, I'll kind of, 60 minutes, excuse me, I'll try and kind of walk through what we should be seeing in this case. But basically, obviously the call proceeded and it went through just fine. So this collected trace that we should be seeing is that we would have the initial invite from 10.1.5.200, and we'd get the trying indicator, progress indicator from call manager. Remember, those 100 type messages are just, okay, I understand what you're trying to do. It's a valid request. Give me a minute to go ahead and process that request, and I'll get back to you, kind of thing. Right, and then we send the invite, forward the invite over to 10.1.5.252, which is that other PSTN destination, and it's going to do the same thing. It's going to send a trying message back to call manager saying, okay, now I'm trying to ring the phone. Give me a minute. I'll let you know what's happening. And then I should get some sort of session progress indicator saying that the session is proceeding and that we've negotiated the appropriate codecs. In the SDP information, we would see an RTP AVP and then a 0 and a 101, indicating that we're supporting the MU-law, G711 MU-law, and the RTP NTE payload information. All right, then we get the ringing, 180 ringing, which again is a kind of an intermediate process, that ring back that goes back to the CIPC1. We get the OK message when the call goes off hook, the acknowledgement, and then the final OK message. And those OK messages indicate that the call, the media stream was able to be established, and we would see that on both sides of the communication channel. That's ideally what we want to see in these traces. So I'll pause the video one more time just so we can take a look at that if it happens to pop up, and we'll take a look at that. All right, so we got our trace information here, and I did get the actual trace here. So we have the invite, like I said. We're going to try to place the call. I'm going to send the invite over to 252, and it's going to give me a 100 trying message. This is going to indicate the session progress. And again, in that session progress, we should see that we've chosen 0101, and that was also what we should have seen. Whoops, didn't mean to close that there. That's also what we should have seen in the initial invite message from this CIPC endpoint on this side, right? So we see actually several different supported codecs, but at least 0 and 101 are in the list, okay? And as such, the call's allowed to proceed. And I keep closing it, but let me go back, pull this up. The call's allowed to proceed. We do our ringing, that's our ring back to the CIPC. The call goes off hook. We establish the call. There's some updates to the call, and then eventually I hung up the call, and we saw that the call terminated. So again, this means that we've basically fixed the problem, basically. All right. So that's, this is one tool that we have available to us to be able to kind of analyze these traces as well. We could have seen a similar set of transactions in a Wireshark capture, but the problem with the Wireshark capture is that depending on where we're doing that capture will depend on what messages we actually see, because you have to remember that call manager is kind of in the middle of this conversation. So the RTMT tool is very useful for being able to collect this information. All right, so we're going to go ahead and wrap up this discovery. We've got a couple more topics that we're going to get into right now, comparing the call control protocols, and then describing DTMF signaling over the IP network. And then we have our summary challenge, so we'll see you guys there. All right, so now let's take a look at, in our last couple of sections in this topic here, in this particular module, kind of the different control protocols. We spent a little bit of time before talking about the difference between the media streaming protocols and the difference between the call control protocols. And we spent a lot of time talking about SIP, the Session Initiation Protocol, but we didn't really spend too much time talking about H323 or Skinny or MGCP, which are the other kind of most common control protocols that you're going to see within a Cisco UC environment, right? So the first protocol we'll talk about here is H323. Now the book doesn't really get into a whole lot of detail on the protocol itself. It is an open standard protocol. It's an ITU telecommunications standardization sector protocol. And it's primarily used for AV type of communication. And it's been around quite some time, actually well before Cisco was doing anything with voice over IP. But it's very widely implemented primarily on mostly video conferencing solutions. And it is kind of the de facto standard when it comes to implementing audio and video functionality on third-party devices. But within the scope of Cisco, we don't really see too often implementations of H323 based endpoints unless they're a gateway. right? In fact, the two primary gateway protocols that we see within the Cisco environment is either an H323 gateway or an MGCP gateway, and we'll talk about MGCP a little bit later on. All right, now this standard H323 is of course part of the H.32x series of protocols, which originally was used to address the need for multimedia communications over ISDN. That is the Integrated Services Digital Network for digital transmission of voice, video, and data over what we call digitalized circuits in the PSTN, and that's been around since the 80s. Also over 3G mobile networks, over SS7 networks. SS7 is another kind of legacy protocol standard that was developed in the 70s for PSTN communication called signaling system number 7. But H323 call signaling is based on recommendations from the ITUT for the Q.931 protocol suite. And the idea is that it really supports all kinds of mixed transports, IP, PSTN, ISDN, QSIG as well, over ISDN, and so on. So in the context of the Cisco world, H323 is really just a protocol that we use to manage gateways. But again, it's not to say that we couldn't have H323 endpoints registered to the system, but the typical H323 endpoint is going to have all of the call control capabilities, all of the management capabilities are going to be controlled at the endpoint level and not at the UC level. So that's the major difference, say, for example, between an MGCP gateway, which has all of its configurations and controls managed by a call manager, as opposed to an H323 gateway, which has all of its implementations managed at the gateway level. All right, so there are a kind of a whole suite of sub-protocols within this macrocosm of protocols that H323 provides. There's an H225 registration, admission, and status protocol. That's going to be used between H323 endpoints and gatekeepers to provide things like address resolution, call admission control services, and so on. There's an H225 call signaling protocol, which is used between different H323 endpoints to establish communication, and that's primarily going to be based on the old ISDN Q.931 specifications. There's an H245 protocol as well, and that is the subcomponent that describes essentially how messages and processes are used for doing things like capabilities exchange, opening up sessions, closing sessions for all types of multimedia transmissions, whether it's audio, video, or data, or even control functionality. There are some other sub-protocols that could be implemented as well. We don't need to get into those specifically, but there's a whole suite of protocols that are available. H235, H239, H450, H460, and so on. Now, H323 also utilizes a series of codecs that are available for the protocol itself. For audio, we can use G711, G729, G729A, 722, AACLD. These are the different, kind of standard codecs that we would typically see with most Cisco implementations, at least. With video, we have H261, H263, H264, and H265. So, the overall architecture of the protocol itself is relatively straightforward. There are terminal control and management sub-protocols, like I said, 255 RAS, 255 call signaling, and 245. There's media control, which is our audio codecs and our video codecs, and then of course our media transport functions, right? RTP, rtcp, that's going to run over UDP, By the way, most of those other terminal control and management protocols, they're going to be either TCP based. 225 call signaling can run over TCP or UDP. 245 can run over TCP. And 225 RAS runs over UDP. And then we have our data applications, which we don't really get into because we're not necessarily concerned about the function of data over H323 when it comes to a voice over IP environment. All right, so there's another component, and we've made mention of this a couple of times already, called a multi-point control unit, or an MCU. And we typically talk about MCUs in the context of H323 because it is a major component, or kind of a terminal component, to the H323 system. MCUs are responsible for managing multi-point conferences. There's a multi-point controller called the MC, and then there's a multi-point processor called the MP. Basically, an MCU is really just a conference bridge that we have that supports multiple codecs, and it supports the ability to join different types of conversations together. The biggest difference in the context of H323 is that H323 MCUs have the capability of dealing with video, audio, and additional data components because it is based on the H323 protocol. So it's basically kind of a multi-point collaboration platform. So you could place a video call, you can place an audio call, and so on. Now, in the context of Cisco, like I said, the most common implementation of H323 is going to be in the gateway functionality. A gateway within the context of the UC system is a platform that provides connectivity between the voice over IP environment, or the IP telephony environment, and the traditional PSTN environment. Although I will say that we have the ability now to bridge IP environments using a cube, a Cisco Unified Border Element, and also utilizing an IP telephony service provider, so IPTSP. And then the IP telephony service provider would provide that session border controller that we could communicate with to do IP end-to-end. Now, granted, I will say that most ITSPs are going to be running SIP, but there is an option for H323 as well. All right. Now, H323 again is recommended by the ITU T, and it defines all kinds of standards, including voice, video, and data, but it doesn't provide any guarantee of quality of service. So, in fact, H323 doesn't even require the use of IP, although most implementations do fall within that scope. SIP is a little bit different, right? The SIP is a protocol that kind of allows us to articulate a method for establishing and terminating those sessions. That's why it's called the Session Initiation Protocol. And there are some pluses and minuses to these protocols. Both of the protocols were developed around the same time. They were developed, I think, in the early 90s or the mid 90s, although there was an RFC in the early 2000s that kind of updated SIP. But also in 2005 or 2006, H323 was updated as well. All right. Like Simple was added to SIP, Dual Video was added to SIP, and so on. All right. And H323, kind of in ideal conditions, has a lot of similarities to what we see with SIP. But obviously in most modern implementations, SIP provides kind of more simplicity. The underlying SIP protocol only includes 6 kind of methods of communicating. It has independence of the transport layer. It could use UDP, it could use TCP, it could run directly over ATM or some other layer 2 transport. It's also much more scalable. The structure that's based on a SIP protocol can increase the number of endpoints significantly over H323. Also, SIP is a very extensible protocol. The protocol is actually defined as a highly extensible protocol, which means that we can implement new features anytime we need to and so on. So SIP is also runs in what we call a human readable format. So SIP is a little bit simpler than H323 when you're developing and creating APIs or interfaces that are going to run with SIP, and that's why SIP has kind of basically become the standard, if you will, these days. All right. Now SCCP, the Cisco or Skinny Client Control Protocol, is a proprietary protocol. It was developed by Celsius. Celsius was the company that developed this technology, this IP telephony technology. It was founded by a couple of folks I believe they were in Texas, in Dallas, Texas. And then they were acquired by Cisco in 1997 or 1998. I think it was 1998. But they obviously created this IP PBX system that Cisco acquired, and Celsius was kind of the brainchild, if you will, and they're the ones that came up with this Skinny client control protocol, primarily originally to communicate with analog gateways, but then they started using it to communicate with endpoints as well. All right, I don't even recall how much Cisco paid for Celsius, but compared to the revenue that they've generated, it was certainly not a lot. But anyway, the Skinny Client Control Protocol was primarily the protocol that was used to communicate signaling information to the endpoints, and it's actually designed to be very similar to the Media Gateway Control Protocol. Basically, it decomposes the function of the overall media conversation into kind of a client-server type of communication process, where the endpoints are basically dumb endpoints, and Call Manager makes all of the decisions on behalf of the endpoint. So every transaction, every event that occurs on the device, messaging gets sent back to Call Manager, and Call Manager makes a decision as to what to do with that particular function. All right. It is based on, obviously, TCP/IP, and of course it uses the real-time transport protocol to carry our real-time audio stream. But SCCP is, like I said, it's kind of a stimulus-based protocol where the clients don't really make a whole lot of decisions independently. They send all of their information back to Call Manager. Because the protocol is proprietary, it's kind of been quickly replaced with SIP and other protocols like H323. So we don't see too much about SCCP these days, but you do have some of the legacy phones that do support SCCP. All right. So just to kind of summarize what we're seeing on the slide here, H323 advantages and disadvantages. It is a standard protocol, but it does provide a peer-to-peer architecture, meaning that the clients themselves have the intelligence. So each client has to be configured with that intelligence to be able to make decisions locally on how it's going to communicate. It's obviously supported by lots of different vendors because it is an open standard protocol. The disadvantage is binary encoding of signaling messages makes it tough to troubleshoot, so we're not using kind of a standard human readable format of communicating. I kind of mentioned that. It's a very stable and mature protocol. It's been around since really kind of the 70s if you look at the pedigree of the protocol itself. H323 represents a suite of protocols. And that's probably the most confusing aspect about this macro protocol, if you will, is that there are a whole bunch of micro protocols that kind of fall under that category. So it is, like I said, an ITUT standard based on Q.931. It uses TCP port 1718, UDP port 1719, and TCP port 1720, and is different than MGCP in that MGCP is a client-server-based protocol, not a peer-to-peer protocol. All right, and again, like I said, it's not typically supported on Cisco phones. It's typically going to be a gateway or some sort of video conferencing endpoint. The advantages of SCCP, the protocol itself from an endpoint perspective is relatively simple. If you're deploying an SCCP device, all of the control functionality and all of the decisions for communicating are based on call manager and based on how call manager is configured. But the downside, obviously, is that it is a proprietary protocol. So it doesn't work with non-Cisco equipment, if you will. All right. All right. So the other protocol that we see listed here is MGCP, the Media Gateway Control Protocol. As the name implies, it is a gateway control protocol as opposed to like a device or phone control protocol. It is another signaling protocol, and it typically is used to control our gateways. There are two primary ways that you can implement a gateway within Cisco Unified Communications Manager. You can deploy the gateway as a H323 gateway, where all of the configuration and control is configured on the gateway itself, including dial plan in the configuration context of what we call dial peers, both VoIP and PSTN dial peers or POTS dial peers, as well as dial plan class of restrictions, core lists and cores and class of our calling restrictions, and also manipulation using transformation elements, right? Transformation patterns or transformation rule sets. So we'll get into that a little bit later on as we start to get into configuring the gateways. All right. Now, the protocol actually is the successor to a simple gateway control protocol, which was actually developed by Cisco way back in the day. But MGCP is a text-based protocol. It does actually use SDP, the session description protocol that we talked about within the context of SIP, for negotiating those media streams and then ultimately to establish the real-time transport protocol stream for the transport of the media. All right. It is a master-slave protocol, much like SCCP. So the media gateways themselves are controlled by call manager as the call control agent. The controller is the media gateway controller, or in the case of Unified Communications Manager, it's simply called the call agent. And then we have various commands and functions that are used between the gateway and call manager to provide things like notifications, reports, status information, configuration data to the gateway as well. The nice thing about implementing an MGCP gateway is that all of the control functionality is done all of the control and configuration is done in call manager and there's very little that you have to actually configure on the gateway itself. So the gateway takes very little configuration. The port numbers that we typically use are 2427, and the call agent will use 2727. But the protocol actually defines 9 standard commands for communicating. They're basically what we call AU commands, or CR commands, or DL commands, or there's a 4-letter command basically that we use, and they're defined, I guess, if you will, as verbs. Basically, it's almost like a SIP notify or a SIP, like a SIP message that you would see. We have AUEP, which is to audit the endpoint. We have AUCX, which is to audit the connection. Those are verbs that are used to query essentially the state of the endpoint and what types of connections are active on that particular endpoint at that time. We have CRCX, which is to create a connection. We have DLCX, which is to delete a connection. We have MDCX, which is to modify a connection. So those verbs are used to manage the connections that are going to that particular gateway. And I think the names themselves kind of imply what their general function is. We also have a request for notification, RQNT, and that's basically a request for notification of any type of events that are occurring on the endpoint. So was the call connected? Was the call hung up? I mean, basically any kind of change in the MGCP communication channel is going to generate an RQNT, a request for notification. We also have a notify, NTFY. This basically says the gateway says, hey, call manager, I detected a change. And so a notify is kind of a response to an RQNT in a sense. Remember, the RQNT is the request for notification. And then we have a EPCF, which is our endpoint configuration. And that's to modify the configuration of the endpoint. And then finally we have an RSIP, which is a restart in progress. I haven't seen that one too often. But that means that basically the endpoint is telling the call agent, hey, I'm restarting. So, as a protocol, it's very similar to SIP in that it uses STP. It has these kind of 9 standard message formats, but it is a very, very chatty protocol. If you were looking at the transactions that occur between an MGCP gateway and call manager doing debug MGCP events or something like that on the gateway, you would see that there's constant communication between the server, which is Unified Communications Manager, and the client, which is the gateway itself. All right. Now, the advantage, a lot of people say the advantage of using MGCP. Let me go ahead and scroll down here so we can see that information. The advantages of using MGCP is that it does provide for centralized configuration, meaning that there's minimal configuration that has to occur on the endpoint, but that also limits kind of the capabilities that you have on the endpoint itself. For example, if you have a desire to do digit manipulation or some sort of DAO plan control on the gateway, you don't have that capability because there are no DAO peers, there is no digit manipulation that you can configure on the gateway because everything is controlled by call manager. But the plus side to that is that there's not a whole lot that you actually have to configure on the gateway to be able to get it to communicate. There's only about 4 or 5 commands that you have to put on an MGCP gateway in order for it to communicate with call manager. But it does also become very reliant on the call manager configuration. All right. Now, as far as SIP goes, I'm not going to get into the details of SIP again because we already kind of went through the details of that protocol. We'll just kind of hit the advantages and disadvantages. Obviously, SIP is kind of probably one of the most widely used media protocols available today. It is ASCII based, so it's very easy to look at SIP traces and understand the transactions that are occurring between SIP endpoints. It utilizes HTTP formatting, DNS, RTP, and of course it's supported on just about every platform that is implementing voice over IP. The disadvantages is you need more bandwidth to do the text-based signaling, the ASCII text-based signaling as opposed to binary signaling, and SIP is still evolving. It's changing quite a bit, but within the context of Cisco, I don't think that's as much of a concern because we're not utilizing all of those kind of new features of SIP these days. We're focused mainly on its ability to act as a voice over IP control protocol for an endpoint. All right. So that kind of gives you an idea. This slide is actually pretty good because it does give you an idea of the different protocols that are used by the Unified Communications Manager platform. And this is pretty much it. These are the 4 primary control protocols that you're going to see in Call Manager: Skinny, SIP, H323, and MGCP. All right. Which signaling protocol is recommended when using Cisco endpoints? When using Cisco endpoints, the protocol that's recommended is SIP, simply because it's open standard and it provides essentially the kind of that standard communication process. And we talked about obviously the benefits of SIP as a protocol itself. So that's what I would say for that particular answer. All right, we got one more section here and then we'll wrap up this lesson. Let's talk about the dual tone multi-frequency component. Simply put, this is when you push the buttons on the phone, they make those funny noises and allows us to provide some sort of signaling control over the channel, over the voice channel, and obviously we use this to indicate characters or numbers that are being pushed on the dial pad to either navigate through an auto attendant or to enter information during the call, data information, if you will. It is called dual tone multi-frequency signaling because you can see here from this graph there is a tone matrix that gets created, and that tone matrix is what allows us to create this multi-frequency system for signaling with the telephony network. All right. Prior to having DTMF, we were using loop disconnected signaling, which was pulse code dialing. I know Andy's old enough to remember that, and Tim is, but some of you may not be. We actually used to use pulse dialing in the US by interrupting the current in the telephone line loop so that we could identify numbers that were being dialed and so on. That was basically that rotary dial that spins back to its resting position after you rotate it to the desired number. And you'd always hate people that had like zeros in their number or 9 in their number because you'd have to wait forever for it to go around. But the multi-frequency signaling is a more of a digital representation, if you will, although it's not technically digital, but it actually represents 16 different signals. There are 10 digits, and then there are letters A through D as well, and then you also have the symbols, the pound sign and the asterisk, which allow us to generate audible tones in the voice frequency range that get transmitted through the line so that we can identify the number that's being pushed. All right. So originally I talked about, you know, these telephones could be used as a computer, or, you know, to provide some sort of automated response, and that's why how they came up with this concept. So the keypad itself is laid out as a matrix with the push buttons. Each row represents the low frequency component, and then each column represents the high frequency component of the DTMF signal. So you have the most typical keypads are going to use 4 rows and 3 columns, but some of them will have a 4th column for specific applications. This is your typical keypad that you see here, obviously. Pressing a key in this particular case sends a combination of that row and column frequencies. So for example, if you press a 1 key, it produces a superimposition of the 697 hertz low tone and the 1209 hertz high tone. You can see the matrix here that describes that functionality. Now keep in mind, this was done you know, obviously kind of as an analog function, right? I mean, we're literally talking about generating frequencies on the system itself. So we now have to emulate this when we're talking about voice over IP. This DTMF concept needs to be somehow incorporated into a voice over IP environment, much like we're emulating things like ringtones, ringback functions, and all the enunciator messages, all of the information that allows us to identify what's happening in the voice over IP environment that we traditionally did with analog functionality has to be now digitally recreated. And DTMF is not something that we can get away from. We use DTMF for navigating through auto attendance, or what we call interactive voice response systems. You know, press 1 for sales, press 2 for engineering, press 3 for human resources, etc. All right. So the DTMF function has to be carried over into this voice over IP environment. All right. Now DTMF is transported typically within the stream itself. It does depend on which control protocol you're using as to which type of DTMF options you have. And the book does break down different options. We can do DTMF in band, or we can do DTMF out of band. All right, it just depends, you know. So within the RTP media stream or outside of the RTP media stream. Obviously, one has more benefits over the other, but let's take a look at some of the different supported DTMF types. So if I'm running H323 as a protocol, you can see I have basically 4 options for supporting DTMF. I would say none is, well, I guess could technically be the 5th option, right? DTMF is not carried out of band. It's basically just carried in band with the RTP audio. And that's in an H323 setting, that's the default. We have the proprietary Cisco option where the tones are sent within the RTP channel, but it's sent as voice data. The DTMF tones are encoded slightly differently from the voice samples because they have a different payload type. Remember, one of the functions or one of the components in an RTP header is to identify the payload type. So if I have a payload type of 121, that's going to indicate that I'm using, that this is a DTMF encoded signal. All right, so I can basically identify the difference between DTMF and regular RTP media by looking at that payload type. All right, the H245 signaling is an out-of-band function. It separates the DTMF digits from the voice stream, and it sends them through an H245 signaling channel and not inside of the media channel itself. They're transported as Input indication messages, we don't really need to get into the specifics of that, but H.245 is an out-of-band mechanism. All right. And the DTMF tones are generated, and of course H.245 is TCP based, so those we have some sort of guarantee of delivery and acknowledgement of delivery and so on. All right. They do mention here, in contrast to H.245 alphanumeric, H.245 signal passes along tone length information, addressing the potential problem with the alphanumeric method. Alphanumeric is basically just telling you what button was pushed. It doesn't indicate how long that button was pushed. H.245 alphanumeric separates the DTMF signal from the media stream as well, but the tones get transported same way as input indication messages, but we don't have any tone length information. I'm not sure that the tone length component is that important, you know, as long as we recognize the tone, but you know, there are some systems that may require you know, length information as part of the DTMF signaling. So you would want to use H.245 signaling as opposed to H.245 alphanumeric. All right. We also have NTE, what we call named telephony events. That's the DTMF tones are going to be transported inside of RTP packets, and that's why it's called NTP RTP typically when you see it referenced in the configuration. And we use those RTP packets to transport the DTMF. But the endpoints are able to negotiate or identify the difference between standard RTP audio and the NTP RTP packets that are used for DTMF, because again, we're identifying a different payload type value for those NTE RTP packets themselves. All right, as far as supporting DTMF for SIP, we have only a couple of options. We have SIP notify, where we use these the SIP notify messages out of band to relay the messages that are that represent those DTMF events during the call. We send an invite message with a SIP call info header to indicate that we're going to use that notify based out-of-band DTMF relay option. And we will either acknowledge that with a 18X or a 200 response message, which uses the call info header. And then the DTMF, once the DTMF button is pushed or once the DTMF signal is generated, we send a SIP notify message for that particular event. After the SIP invite, and then we can identify the DTMF transactions based on that. We also have named telephony events within SIP as well. That means that we're going to go ahead and transport the DTMF inside of RTP, again with a different payload type value for those specific NTE RTP packets. All right. You know, what I've found in my experience in dealing with DTMF is pretty much the defaults work in most environments, but there may be occasions where you have to utilize a different DTMF encoding method. Maybe the ITSP requires a specific type of DTMF encoding. And really the choices you have are in-band or out-of-band, and then you have a couple of options with regard to how the events are transacted. With SIP, though, you really only have the two choices, so it makes it relatively simple. If one option doesn't work, use the other option. So it's pretty straightforward. You can see in MGCP, we also have 5 different options. In-band, just kind of incorporating the DTMF signal inside of the RTP audio stream is the default, much like H323. We also have the Cisco proprietary option, which is also an in-band option, but the coding for the DTMF signals are different because we're able to identify them with the payload type. We also have named signaling events. that transports the DTMF information within RTP using these named telephony events. We also have named telephony events in gateway controlled mode and call agent control mode, and then finally out of band signaling. So again, I'm not going to get into the specifics of each of those, but you can see that there are a multitude of ways of transporting DTMF. And they do ask you about it a little bit on the exam. You guys have probably seen that in some of your review questions, but for the most part, because we're dealing with SIP, we don't really have to worry too much. Well, really the only two that I would typically see are SIP for my endpoints, for DTMF on my endpoints, and H323 for my gateways. But even my gateways can be deployed as SIP gateways as well. So, you know, we can kind of standardize on SIP as our primary protocol. All right. What is the tone that is generated on a touch tone phone when keypad digits are pressed called? I don't know what that's supposed to mean. What is the tone that is generated on a touch tone phone when the keypad digits are pressed called? Okay, well, that doesn't make any sense, but basically that code is our DTMF code, right? Our dual tone multi-frequency code. All right. Oh, I see. What is it called? I get it. All right. It's kind of a weird way of writing the sentence, but yeah, they're called DTMF tones, dual tone multi-frequency tones. All right. All right. So let's get into our summary challenge. So the first question in our summary challenge is, which of the following is the process of checking for available bandwidth before allowing the call to proceed? Checking for available bandwidth before allowing the call to proceed is call admission control. And again, like I stated before, there's a couple of ways we can do this. We can do this utilizing the process of localization, or excuse me, localized call admission control on the call manager server with the use of locations and regions. We can also do RSVP based call admission control. RSVP is the resource reservation protocol, which allows us to guarantee bandwidth for a particular call based on QoS reservations. Or we can also do gatekeeper controlled call admission control, where we have an actual H323 network and H323 gateways, and they're reporting the different types of calls that are being processed at the time. And we have a gatekeeper that kind of manages that domain and says, yes, the call can proceed, or no, the call can't proceed based on lack of available resources. All right. In a Cisco collaboration solution deployment, which of the following endpoints are supported by the H323 standard? In the case of Cisco, it's going to be mostly our gateways. All right. As far as a endpoint, we can do H323 devices, H323 video endpoints and audio endpoints, but it's not very typical within Cisco. Certainly the desktop phones don't support H323. Some video endpoints, third-party video endpoints do, but not Cisco video endpoints, and certainly not analog endpoints. All right, the SCCP protocol is best defined as, well, it is not a standard-based protocol, so A and D are out. Proprietary voice based on RTP. Well, all of the protocols result in some sort of RTP media stream. RTP is kind of separate from the control protocol. It's independent of the control protocol. So it is a proprietary voice protocol that's used for call signaling, like SIP, like H323, like MGCP. All right. What aspect of the MGCP protocol creates a single point of failure? Well, MGCP is reliant solely on Call Manager. As a client-server-based protocol, Unified Communications Manager or Call Manager is the device that is providing that control. So if Call Manager goes down, the MGCP gateway cannot act independently, as opposed to an H323 gateway. There's a feature within Cisco Unified Communications called SRST, Survivable Remote Site Telephony. SRST is a iOS gateway that can act as a telephony call control agent or phone system, basically, in the event that the primary call agent or call manager is not available. And in order for a gateway to act, an ISR router to act as a phone system, it has to be operating in H323 mode, because that's H323 allows complete control of the dial plan, of the signaling for PSTN connectivity, and so on the gateway directly. Whereas with an MGCP gateway, even the signaling for PRIs or T1 CAS circuits are going to be sent back to call manager. The data link layer and the physical layer is managed at the gateway level, but the layer 3 layer is managed, the network layer is managed at call manager. So if call manager goes down, you can't even manage the Q931 messages or the layer 3 functions of your digital circuits. All right. Which SIP message notification number is used to notify the calling party that the called party is ringing? So this is kind of one of those annoying little questions that you kind of have to just memorize. In this case, it happens to be 180 is the message that indicates that the called party is ringing. All right, 404 and 503 are bad messages. All right, which protocol did the IETF develop as an alternative to H323? And that is SIP, all right, the Session Initiation Protocol. And then finally, which of the following is the DTMF relay method that all H323 version 2 compliant systems are required to support? We actually saw this in our discussion. It was, I don't even think I mentioned it. It was in the body of the text, but it's H245 alphanumeric is the answer in this particular case. Remember, alphanumeric allows us to identify at a minimum that a DTMF code was pressed, whereas H245 signal provides information about the timing of that as well. All right, so at a minimum we need to know at least that a particular button was pressed, which kind of makes sense, right? Alphanumeric really describes the keypad itself, and that's the whole concept of DTMF, is to be able to identify the numbers and the letters that are pushed on the keypad. Each key has a corresponding letter, actually a group of letters, and then numbers as well. All right, so we'll wrap up this module. We're going to move into our next module, which is integrating Cisco Unified Communications Manager with LDAP.